Global Technical Standard Training from Jeff, JAKA Overseas Support Director.
Hardware introduction of JAKA robot. This course will be divided in 4 parts. 1. Introduction to installation. 2. Introduction of the robot. 3. Cabinet introduction. And 4. Introduction to the control stick handle. The time of the course will be around 20 minutes, and the main objectives are 1. Robot installation wiring. 2. Preliminary understanding of robot body and controller. 3. Cabinet switch on and off, power on and off, enable and disable with the control stick. Let's start. Part 1. Introduction of installation. Let's take a look at the robot unpacking and installation video. First, take out the robot from the packing box and install it on a fixed base. Fix the control cabinet and connect the heavy cable of the robot with the hexagon screw in advance. Connect the robot control stick wire. Then connect the external rotor. Take down and route the network cable through the cable hole and connect the network cable to the bottom network port. Then you can connect the power supply, release the emergency button stop, and connect the pad to the wireless network. Then open the software, click the connect button, select the robot, input the administrator password, JAKA_admin. Then you can turn on the power and start the robot. The installation is complete. The 3 robot is fixed with a 4 M625 inner hexagon screw. The 7, the 12, the 18 are fixed with 4 M825 inner hexagon screws. The mini Kobo is secured with 4 M6 16 hexagon screws. On the right, we can see the bottom of our control cabinet. It is successively Ethernet cable interface, body heavy-duty interface, handle line interface, and power switch 220 volt power interface. Part 2. Introduction of robot. The robot body is a moving component to achieve the desired action of the user. At the same time, the end of the body does not really indicate the state of the robot. The button for dragging and programming, the I/O interface and the TIO interface connecting the end tools. The cabinet contains core computing components and a variety of electrical interfaces. At the same time, the cabinet is equipped with a handle to facilitate user operation. The wireless network port of the cabinet should be connected to the router, and the operating terminal should also be connected to the wireless network of the router. It is recommended to configure a separate router for the JAKA Zoo series robot to prevent conflicts with other devices. In the operation, the single graphics card provides JAKA Zoo series robot operating software based on Android system. The recommended operating hardware configuration of the software is shown in the table. When users purchase JAKA Zoo robot, they can also demand to purchase an operating terminal or use their own tablet computer. In the schematic diagram of Zoo robot arm, it includes 6 joints and 2 connecting rods of the big arm and the forearm. The joints 1 to 6 are respectively from the base to the head of the robot. The head of the robot is equipped with 1 button and a breathing light. The JAKA Zoo has hand indicator and a pause button. Breathing light with the position of the button is shown in the figure. Its colors meanings is as shown in the table. Blue is powered on state. Green represents enabled, so the robot is ready. Red represents fault. Yellow is a free drive mode. Flashing yellow is a pause mode. Machine end button press the end button when the robot is running. It can suspend the robot movement. And press it again to resume the motion. The use of the end pause button requires the user to fully access the possible risks. Sudden start and stop of the robot may cause personal injury or equipment damage. Mechanical end flange button is equipped with the tool I/O interface and 2 buttons on the outside of the flange. The buttons are free drive button and a position recording button as shown in the figure. When the free drive button is pressed, the drag instruction mode is entered. Point button. After the user directly drags the robot to set the desired position, press the button to record the point position. The operating software records the corresponding position and creates a teach point directly into programming page. The end of the robot has a TIO interface, which can interact with external devices for signal connection. The TIO external interface of the tool side is defined as shown in the right table. Pin 1 is 24 volt plus, and Pin 2 and 3 are digital input NPN. Pin 4 and 5 are digital output NPN type. Pin 6 and pin 7 are the positive and negative terminals of the analog quantity. And finally, pin 8 is a 24 volt power supply negative. Part 3. Cabinet introduction. Cabinet 2.1 internal ports cabinet has 8 types of external ports. P1 and P3 are digital ports. P and PI electronic frequency effective. P2 and P4 are digital quantity output ports. P5 has 2 configurable analog ports and P6 is a high-speed input. P7 remote switch and RS485 communication interface. P8 is a safety function, namely internal 24 volt power interface. P9 USB interface and P10 Ethernet interface. P1, P3 are digital input interfaces, used to connect various sensors, switch buttons, etc. P2, P4 digital output interface, used for digital signal output or control solenoid valve, indicator light for example. P5, 2 configurable analog interfaces are used to collect analog signal or control devices. P6, high-speed input interface for collecting high-speed encoder signals. P7 terminal remote switching on-off machine and RS485 for Modbus RTU communication. P8 safety function and internal 24 volt power interface for front safety signal configuration. P9 3.0 USB port for UV connection, USB flash drive and other storage devices. P10 Ethernet interface used to connect router or open network communication. Minicab monitoring introduction. Minicab typically used a minicab controller, external DC power controller, handle and operation terminal. Note that the minicab needs to be installed in a well-ventilated dry place and cooled by natural convection. When the heat generated in the use scenario is high, if the cobot body runs at fast speed at a large load of frequency break, external fans are required to cool the minicab. The definition of user interface pin is shown in a figure. Include power pin, remote power on-off pin, digital I/O pin, detection pin, 485 master station pin, and RS485 slave station pin. DC power input terminal. Pin 1 is the input of logic electric power supply. Pin 2 is the input of robot power supply. And pin 3 is ground. Do not connect the negative terminal. The user power supply can be generally divided into 3 categories. The first, 48 volt switching power supply. The second, lithium battery. The third, 24 volt power module is used with the minicab. The following figures show the power supply specification of JAKA Zoo robot. The rated voltage of a 48 volt and the voltage range is between 30 and 60 volts. Zoo 3 has a peak power of 900 watt and a 1000 watt switching power supply is recommended. The peak power of the initial robot is 1800 watt. And it is recommended to use 2 1000 watt switching power supplies. Zoo 12, Zoo 18 peak power at 3 kW. 1 kW switching power supplies are recommended, or 48 volt lithium battery can be used. Minikobo is 24 volt power module provided by JAKA. Be careful not to connect the negative terminal. The figure on the right shows the controller handle of Minikobo. If you do not need an external handle, you need to add the minicab collective adapter. The minicab is delivered with a handle by default. If an adapter plug is required before delivery, a note must be made before delivery. Emergency stop. You can use the set stop button on the controller handle. It can be connected to the external stop panel. Support a separate emergency stop connector, which is a short-circuited to the internal 24 volt. On the first panel, press the power button for 1 second and then release the electric control cabinet to start up. The display will be red, blue and green alternatively. After the start, the cabinet will bring blue and shut down. Second way, through the handle to start and shut down, short press the start button for 1 second and then release. The buzzer rings, the electric control cabinet starts to shut down. Long press the start button for more than 3 seconds, the handle buzzes 6 to 7 times. The electric control is not shut down. The third way, through I/O remote switch machine. Remote boot requires the user to provide external 24 volt DC power supply separately. Connect the positive pole to the power supply to the remote boot interface of pin 8 and the negative pole to the pin 6 grounding interface. Press the switch for about 1 second and release the electric control to start and shut down. Remote shutdown needs to connect the positive pole of power supply to pin 5. Remote shutdown interface. The negative pole is connected to the P6 grounding interface. Can use external power supply and also use internal 24 volt power supply. Long press the button for more than 3 seconds to loosen the electric control with shutdown. The wiring diagram of remote switching machine is shown on the right. The braking voltage must be at least 3 volts higher than the input voltage. If the module supply voltage is 48 volt, set the brake voltage to 51 volt. If the 48 volt lithium battery is used for power supply, the voltage is 54.6 volts and the resistance is set. The starting voltage is 58 volts. If the power supply is from a 24 volt module, the input voltage is 24 volt and the automatic resistance starting voltage is 27 volts. Check the automatic resistor starting voltage immediately after online. The minicab supports two network ports, namely LAN 1 and LAN 2. LAN 1 supports 10 GB and LAN 2 supports 10 GB auto-adaptation. Minicab's built-in Wi-Fi hotspot is password-free by default. Users can connect to the minicab through a wireless terminal. After minicab is started, the Wi-Fi indicators on the right side of the panel lights up. When the Wi-Fi is connected, the Wi-Fi indicator turns to blink. The minicab and the robot body can be controlled through the app. The Wi-Fi hotspot name must be the same as the minicab ID. If you need to change the Wi-Fi name or add the login password, please contact JAKA technical support personnel. The satisfaction network can be 1000 MB, 100 MB, adaptive network port, and the factory default configuration is 10.5.5 network segment. When connecting to network port LAN 1, set the device IP address to a range from 10.5.5.1 to 255, or configure the device to dynamically obtain an IP address. If the device does not support IP address change, you are advised to connect the device to network port LAN 1 and set the IP address of network port LAN 2 to the same network segment as the device. If the network can be occupied and you have to use the network port LAN 1, please contact JAKA technical support personnel to modify network port 1. Network can dynamically obtain IP addresses for 10 GB adaptive network port by default. User can log in the app and configure static IP paths to set network setting for the system. Do not set the IP address disconnection of network port LAN 2 to the same as that of network port LAN 1. Otherwise, login may fail. If the LAN port must be set to network segment 10.5.5, contact JAKA technical support personnel to modify the LAN port. Part 4. Introduction to control stick. The figure on the right is a schematic diagram of the controller buttons. Simple functions of the electrical control cabinet and robot can be realized with a handle, such as the start and stop of the electric control cabinet. We can review buttons on the handle: switch on/off button, start/stop button, pause, resume button, enable button, repeat button, and lock button. For handle operation, press the power button for 1 second after startup, and then release after the sound monitoring. If this monitor does not turn on and off, the user will press the button for more than 3 seconds and the handle buzzer for 6 or 7 times to shut down the cabinet. When the power supply is not turned on, press the button to power on the cabinet. When the power is turned on, press the button to power on the robot. To enable the robot, then, press the lock button and enable button simultaneously. When the robot is enabled, press the lock button and enable button to start the program. Short press the start-stop button to start the default program. Press continuously to control the robot movement to set the initial position in the non-running state of the program. When the robot is in an initial position, keep pressing the lock button and wait for the breathing blue light. Pause Restore button during the automatic operation of the robot. Press the pause procedure to restore the robot to the suspended state. You can press the recovery program execution. Lock the handle by long press the lock button for 3 seconds and the indicator will have orange breathing light. Then the buttons are invalid except lock and switch buttons. The app can control the robot and the light will be off when the robot is in an unlocked state. Gray app interface can be used to control the robot. Note that the emergency stop button can be only used in emergency situations, not as a general critical equipment. That is all for the hardware introduction of JAKA robots. Thank you for watching. Check software version and upgrading procedure. This course is mainly about how to upgrade the robot software, including 4 key points. 1. Check software version. 2. Upgrade controller. 3. Upgrade the SCB. 4. Upgrade joint servo. The course duration will be around 8 minutes. Aim to know how to check software version and complete the upgrading according to documents. Part 1. We'll go through how to check the software version. First, we need to connect the tablet to the same network with the electrical cabinet. Open the JAKA Zoo app and click on the disconnect icon at the top right corner. Find the correct robot and connect it. Regarding the version 2.1 electrical cabinet, it is equipped with internal Wi-Fi module. Use handle to start up the cabinet. Wait until the light turns blue. It means that the cabinet has been started up. Notice that the tablet will find a Wi-Fi network with CAB in the name. In case of using internal Wi-Fi, user is allowed to add a router for connection as well. Click Connect and select correct robot in the list. User login window will pop up. In this pop-up window, 3 levels users are provided: administrator, technician, and operator. Administrator will have all the function access, and the technician user will be able to access the robot programming and basic function access. Default password for administrator is JAKA Zoo admin with no capitals. Click the info icon at the bottom right corner. The pop-up window will display current robot software version. From this window, we're able to check those information such as app, servo, CSB, and controller version. Part 2. Upgrading procedure. In the general settings page, we could upgrade the controller and SCB software. Please follow the proper steps when upgrading. The correct steps will be upgrading the controller first, second upgrade the app, third upgrade the SCB, then upgrade the servo and firmware at last. Upgrade the controller. Download the package in local disk, open JAKA Zoo app, ensure the robot is powered off. Then click the settings icon at the top right corner. Enter the upgrade controller screen, click the blank rectangle to find the package downloaded, select and upload it. This package name should be strictly the same with the original downloaded file. When the upgrading completed, the controller will reboot automatically. After controlling upgrading completed, we could start to upgrade the JAKA Zoo app in the pad. If JAKA Zoo app is already installed in the pad, uninstall the old version before installing the new version app. It is important to allow all permission when installing. Upgrade SCB. First, Upgrade the controller. Download the package in local disk, open JAKA Zoo app, ensure the robot is powered off, then click in the settings icon. Enter the upgrade firmware screen, click the blank rectangle, find and upload the package downloaded for upgrading. This package name should be strictly the same with the original downloaded file. Wait until the controller is turned off. Use the handle to start it up. As the CSB is upgrading, the handle is de-energized and the status light will be not lit up. After the controller is started up, we could find the robot and reconnect it. Step 6. Repeat step 3, select the CSB package and re-upload it. Step 7. Wait for the controller power on, then use the handle to start up the controller again. The upgrading is completed. Upgrade servo. Step 1. Download the package in local disk. Step 2. Open JAKA Zoo app. Ensure the robot is powered off and e-stop is released. Step 3. Click the setting icon. Enter the upgrade firmware screen. Click the blank rectangle to find and upload the servo upgrade package. Select and upload it. The package name should be strictly the same with the original downloaded file. Step 4. The controller will energize automatically when upgrading. App will pop up the upgrading process. Wait for a few minutes, the controller will reboot and the upgrading procedure is completed. That is all for this course. Thanks for watching. Preparation before enable robot. This course is mainly about the preparation before enable the robot. It consists in 2 parts. 1. Installation setting. 2. Robot payload setting. The course duration is around 5 minutes and the 2 main goals are 1. Be familiar with the critical parameter setup before enable the robot, and 2. Be able to set up the robot payload correctly. Let's start. Installation setting is provided by the app. By clicking the shortcut icons at the top right, robot pose can be set directly. 3 typical installation: sail mounting, side mounting, and bottom mounting, from left to right. In case of special installation required, directly input the actual installation angle. See if the robot model shown on the screen is the same with the actual installation. Robot payload setting. In general settings, find the payload setting option. The manual input load weight and centroid is supported currently. Payload setting requires the load weight and centroid X, Y, Z offset. Before setting payload, reconfirm the coordinate system of end flange. Firstly, find the TIO connector at the end flange, which is shown as the black hole in the left picture. The X positive direction is from the TIO, perpendicular to the end flange surface, facing out, shown as the red arrow. The Z positive direction is from the connector, parallel to the end flange, facing down, shown as the blue arrow. The Y positive direction is perpendicular to the plane of X and Z composition, shown as the green arrow. The origin of the TCP is the center of the end flange bottom side. As the example in the right side picture, the robot is installed with an electrical gripper. Weight of the gripper is around 0.8 kg, so we input 0.8 kg in the load settings. Then, due to the XY is the same with the flange coordinate system and the Z is offset about 80 mm, we will need to input 0 for X, 0 for Y, and 80 for Z for the centroid settings. In case of centroid Z increasing, the payload will be reduced. The follow charts show the payload offset for each serial robot. This payload offset chart is for Zoo 3. Offset, full payload of Zoo 3 is 3 kilograms. This payload offset chart is for Zoo5. Offset, full payload of Zoo5 is 5 kilograms. This payload offset chart is for Zoo7. Offset, full payload of Zoo7 is 7 kilograms. This payload offset chart is for Zoo12. Offset, full payload of Zoo12 is 12 kilograms. This payload offset chart is for Zoo18. Offset, full payload of Zoo18 is 18 kilograms. This is payload offset chart for the Zoo-FT. Offset, full payload of Zoo-FT is 16 kilograms. Robot collision protection setting. In the safety settings screen, find the collision protection setting option. For normal users, we could select relaxed restriction in the quick setup. Notice that before setting the collision protection, proper installation pose, payload, centering setting are required. In quick setup option, the relaxed restriction or general restriction is recommended. Before enable robot, click Power on the robot. The ring light at the end will turn blue in a few seconds. After robot powered on, click Enable robot. Pop-up window will display the current settings of the payload, installation pose, and collision protection. Ensure those settings are correct. Then click Confirm to activate the robot. Before enable the robot, ensure the electrical cabinet is grounded properly to avoid current leakage. Before enable the robot, ensure all the screws of the robot and flanges are tightened properly. While enable robot, keep operating handle in hands. Press the emergency button if necessary. It's normal that there might be some sound after the robot powered up, and it will swing slightly when enabled. That's all for this course. Thanks for watching. Manual operation. This lesson mainly explains the manual teaching operation of JAKA robot, including the following contents: robot joint teaching, teaching coordinate system selection, position teaching, step teaching, manual input teaching. This class lasts about 15 minutes. Course objective is 1. To understand the teaching method of the robot. 2. To be able to control the robot to move to the target position. JAKA robot is composed of 6 joints. Each joint can move independently. Slide the virtual joystick on the right side of the interface and hold it there. The corresponding robot joint will immediately rotate in the corresponding direction. When the joystick is released, it will return automatically to the origin, and the robot will immediately stop moving. Take a look at the video of the joint teaching below. Drag the joystick to teach points. Then, the movie spin below to control the spin during teaching. The movement speed can be entered manually. The 6 joints of the robot can be taught individually. Note that there is a movement speed directly below the operation interface in the end. When dragging the rightmost 100%, the speed at this time is about 1/3 of the maximum joint speed. The joint position keeps changing after enabling, and the position remains unchanged after enabling. This is a normal phenomenon because after the enabling, the position feedback data of each joint encoder is displayed. After enabling, the data here is the data of the position command. Switch between tool coordinate system and user coordinate system. In order to facilitate teaching, the JAKA robot supports teaching movement in the tool coordinate system and in a user coordinate system. The position of the robot base has the red, green, and blue coordinates, which is the user coordinate system. When the offset of the user coordinate system is all 0, it corresponds to the world coordinate system. Also, there is a red, green, and blue coordinate system at the end tool of the robot, which is the tool coordinate system. And when the offset of the tool system at the end of the robot is all 0, it is the end flange coordinate system. As you can see, there is a button to switch the user coordinate system and the tool coordinate system in the robot teaching interface. After clicking the switch, the corresponding icon on the right will turn red. Now check out the video below. Click the Switch Coordinate System button. You can select the user coordinate system or the tool coordinate system. The user coordinate system can select the world or the 10 user coordinate system in the settings. Tool coordinate is the same. The user coordinate system is a static coordinate system. After adjusting the robot's posture, the direction of the coordinate system remains unchanged. The teaching of the robot is still moving in the original direction, and the tool coordinate system is a dynamic coordinate system. After adjusting the robot's posture, the direction of the coordinate system changes, and the teaching direction of the machine also changes. In the user coordinate system, the end of the robot will move along the coordinate system direction of the boss position, like on the video. Linear motion or rotational motion around a straight line. Sliding the X-axis joystick to the right means moving to the positive X direction. Slide the Y-axis joystick upwards means moving to the positive direction of Y. Let's have a look at the video. In the teach of the X-axis direction in the user coordinate system. Then teaching of the Y direction in the user coordinate system. And at last, let's look at the teaching of the Z in the coordinate system. For the rotation, in the user coordinate system, R-axis rotates and teaches, and the robot rotates around the X-axis. In the user coordinate system, every rotation teaching, the robot makes the Y-axis of the user coordinate system rotation. And finally, in the user coordinate system, RZ rotation teaching, the robots make a rotation around the user coordinate system Z-axis. In the tool coordinate system, the end of the robot will move along the coordinate system direction of the end flange position. Move in a straight line or rotate around a straight line. Sliding the X-axis joystick to the right means moving to the positive X direction of the robot. The same for the Y. Sliding the joystick upwards means moving to the positive Y direction. Okay, now take a look at the video. The X-axis direction teaching under the tool coordinate system. The robot moves along the X-axis of the tool coordinate system. The robot moves along the X-axis direction after the change, and the Y-axis direction it starts in the tool coordinate system. The Y-axis direction changes after switching the robot posture. Teach along the Y-axis, the direction of the robot movement will also change. Then, teaching in the Z-axis direction in the tool coordinate system. Now about the rotation. Eric's rotation teaching in the tool coordinate system, the robot rotates around the tool X-axis. The tool is used as a tool to teach the rotation of RY. So for RY, the robot rotates around the Y-axis of the tool coordinate system. For the RZ, the tool is used as a device to teach RZ rotation. So now the robot will move around the Z-axis of the tool coordinate system. By dragging the movement input bar at the bottom of the manual interface, the speed of the robot movement can be adjusted. You can also click the percentage above the movement bar to enter a specific percentage. Speed joints and the linear motion also support fixed motion, and the step value is on the left and right side respectively. Now take a look at the video. So set the moving speed below, and you can control the speed of the robot. Then you can also select the step value. So choose a step to change the fixed angle, then choose a continuous, and the teaching move will go continuously. After selecting the step value for position teaching, the robot moves a fixed distance. Select continuous for continuous movement, and the more the step value will be small, the more precise movement of the robot will be. Manual input operation. Input the target position, the user coordinate system, the desired target, and let the robot move in a way of joint or linear motion. Click any position information box on the manual operation interface to enter the position movement interface. First, if you need the robot to move to the specific joint motion, enter the end position of the 6 joints in the joint position area. Press and hold to move to this point. The robot moves to the specified position. Click OK to exit the position movement interface and complete the position movement. Second, if the robot needs to move to the specified space position, enter the endpoint space coordinate system in the tool coordinate system position area. The same, click to calculate the joint position, press and hold to move to the point. After entering the target point, you can choose to move to the target by joint or in a straight line. The difference is that there are singularities in linear motion. And any robot has singularities, which is related to the design of the robot. For points that cannot be moved, joint movement is recommended. Watch the video. Enter the Cartesian coordinate system and click Calculate. Move linearly to the specified target point. Enter the x coordinates -50 and click Calculate. When the linear motion reaches the singular point, the robot is protected and stopped to try joint motion. The robot can move normally. The joint motion of the robot can normally move from the place where the x-coordinate system is at 222 to the place where the negative coordinate is equal to -50. Now use linear motion instead, and the robot reports the starting point to protect the stop. Go back to the original place in the same position. The robot can move normally in the way of the joint movement. This is the end of this lesson. Thank you for watching. User coordinate system. This lesson is mainly about JAKA app. The user coordinate system setting mainly includes the following contents. 1. The calibration of user coordinate system. And 2. Application scenarios for user coordinate system. The course lasts about 15 minutes, and the objectives of the course are 1. Be able to calibrate a user coordinate system independently, and 2. Understand the usage scenario of user coordinate system. What is necessary to calibrate user coordinates? Let's look at the first part of the user coordinate system and see why we need to calibrate the user coordinate system. Firstly, the calibration of user coordinate system can facilitate the teaching of point positions. In some application scenario, the direction of robot would coordinate system is not parallel to the working plane. For example, in a tilted working plane shown on the right, it is difficult to teach the point position of the working plane in a world coordinate system. It is convenient to calibrate a user coordinate system parallel to the working plane. Secondly, by setting different coordinate systems in the program, the offset function of the overall motion track is realized. And finally, move in a relative straight line in a specific direction, calibrate the user coordinate system, and move in a relative motion in a user coordinate system to avoid the problem of non-alignment between the relative direction and the direction of the world coordinate system. Before we get to the user coordinate system, let's take a look at the world coordinate system. The default user coordinate system is the world coordinates, which cannot be modified. The world number analysis originally found that the line direction between the center of the base and the interface of the heavy load line is the positive direction of the x-axis of the world coordinate system. The vertical direction of the base refers to the positive direction of the body in front of the camera is the positive direction of the z-axis. And the positive direction of the y-axis of the world coordinate system is determined according to the right-hand spiral value. At the coordinate system of JAKA are the right-hand coordinate system. Use your right hand to make sure that your thumb points the direction of our x. Your middle finger points in the direction of our z. And your index finger points the direction of our world y-axis. User coordinate system in addition to the world coordinate system. JAKA opens up to 10 user coordinate systems with editable parameters for the user. As shown in figure, in our app setting, set user coordinate system operation interface. You can set the parameters of the user coordinate system with 6 parameters. The first 3 parameters for the position and the 3 other parameters for the angles. The angles are expressed in Euler angle coordinate system relative to the world coordinate system. If the user coordinate analysis direction is consistent with the world coordinate system, then the attitude is 3 zeros. 2 methods of setting user coordinate system. First one, input settings. Calculate the desired user position as a system relative to the world according to their own needs. Fill this data into the corresponding data box, then click OK. Second method, the 3-point setting automatically calculates the desired position and attitude parameters of the users by setting 3 position points by the user. The definition of these 3 points: point 1 wants the origin of the user coordinate system. Point 2 wants the position of the positive direction of the x-axis of the user coordinate system. And the point 3 wants any point in the first quadrant of the x-y plane of the user coordinate system. Now, let's watch the video. In the setting interface, you can set the user coordinate system by manually entering our data as a series of parameters. For example, if 100 is entered, it indicates that the z direction of the user coordinate system is shifted upward by 100 millimeters. In the manual view screen, you can see that the user coordinate system has been shifted 100 millimeters upward along the z direction. Now, the second way, the 3 points setup. Click on the first point to set the coordinate system. The first point is the origin of the coordinate system. Set the second point to be any point along the x-axis. Set the third point. The third point is a x or y plane, any point in the first quadrant. Click OK after setting the 3 points to automatically calculate the user coordinate system parameters. The user coordinate system is selected in the manual operation interface, and the robot can be taught in this coordinate system. User coordinator 3 points for setting nodes. A calibration user coordinate system of 3 points, the attitude of the need to keep consistent. The distance between the 2 or 3 points should be as large as possible so that the user coordinate system will be more accurate. The second part, user coordinate system programming applications. First, set the meaning of user coordinate system instruction. Select the user coordinate system that has been set. Click the user coordinate system drop-down list and select the word coordinate system or the 10 user coordinate systems that have been set. Second, set the user coordinate directly. To create a user coordinate system, click the instruction setting interface. You can manually enter the parameters of the user coordinate system or dragging the array variables. Then, relative linear motion in the user coordinate system. You can choose the reference coordinate system. When the reference system is selected as the user coordinate, the straight line motion will be made in the direction of the user coordinate. User coordinate system application case 1. Set different user coordinate system to achieve the overall migration of the motion trajectory. In the interface of setting user coordinate, set 2 user coordinates by manual setting, such as user coordinate system 2 and 3 in the right picture. The offset of Z direction is 50 mm and 100 mm respectively. The following is an example. Firstly, we set the user to make the event of moving 5 points in a straight line. Then, change user coordinate and make the same 5 points, and so on for 3 times. Watch the corresponding motion video. We run the program. So first of all, the robot moves in the world coordinates and do the 5 positions we set in advance. The overall point position of the robot moves upward 50 mm and 100 mm in user coordinate system 3. In this video, we can see that the same program which moves the square has different results after setting the different user coordinates. User coordinate system application case 2. In user coordinate system, the tray movement is realized by relative linear motion instruction. In the setting operation, set user coordinate system interface with a 3 points method to establish the user coordinate system as shown in the right picture. First, set the tray X to count 0. Set the count in the Y direction to 0. Set the distance between the pallet in the X direction to 120 mm and the distance between the pallet in the Y direction to 120 mm. We set the user coordinate just created and set initial position. Let's play the video. Wait for 1 second and set the offset of the array subscript 0 is equal to the program variable x times the program variable delta x. The cluster calculates the distance to the straight line motion x squared. Call down the command. Set the offset of the array element to 1 is equal to y times the distance to the line motion delta y. Make a relative linear motion in advance under the user's matching. Drop 50 mm after the movement is in place, and then rise 50 mm after waiting for 1 second. When the movement is complete, increase the x count by 1, then make a judgment that the x count is equal to 3, reset the x count and increase the y count by 1. If y count is equal to 3, reset y. The program realizes a 3 times 3 pallet instruction by making a relative linear motion under the user's generator. That is the end of this lesson. Thank you for watching.
Tool center point setup. The course content will be 1. Setup of TCP. 2. Application scenario of TCP. 3. TCP calibration. The course duration should be around 20 minutes and the course goals are able to create a TCP and 2. Be familiar with the scenario of TCP and the typical application. First, we'll go through the setup of the tool center point. The advantage of TCP. First, it's very convenient for us to teach points when we need to adjust the robot pose. In a case we don't have a TCP, the robot can only teach around the center or end flange. While the actual tool position might be different after teaching and requires reteach, we could easily solve this with TCP. By setting up different TCP in the program, we could shift the movement path. Third, to let the robot move in a linear around relative to the TCP, the typical application with a 2D vision. Before we start learning TCP, let's look at the end flange TCP. This is the default position for TCP of the robot and its parameter cannot be modified. The origin of the end flange is at the center of the end flange. The opposite direction of the end tool I/O connector is the positive direction of this TCP. The Z positive direction of this TCP is from the center of the end flange towards its outside. The X positive direction of the flange is defined according to the right-handed screw system. Make the gesture as shown in a picture. Point your index to the Y positive direction and the middle finger to the Z positive direction. The X positive direction of the TCP will be the thumb pointed. Besides the end flange TCP, JAKA Robot also provides 10 more editable tool center points. As shown in the right picture, in the TCP settings of the operation setting, we could set up the TCP wanted. There are 6 parameters. In the first 3 parameters are the offset dimensions of the new TCP, comparing to the end flange, while the last 3 are pose parameters. The pose of the new TCP comparing to the end flange TCP in Euler angles, in case of the new TCP pose in the same with the end flange. Those parameters are 0, 0, 0. If you want to set up a new TCP, there is basically 3 methods for that. 1. The manual input. 2. the 4-point settings. 3. The 6-point settings. During the next slides, we're going to see in details these 3 methods. First of these 3 methods, input settings. Comparing the new TCP and the end flange TCP, calculate the offset value of the dimension and pose orientation. Then you can input the results in each of the white rectangles. The second method, the 4-point setting. Find a fixed position as a reference within the robot reachable range. Set those 4 points with different pose while the robot should point aim at this reference point at all positions. After setup of those 4 points, click confirm. The software will calculate the TCP parameter automatically. Now let's watch the video. In the TCP setting in general setting, click the edit icon. In the case of high accuracy is not required, we could input the TCP parameters directly. For example, 200 on the Z-axis. Then you can click confirm. For the 4-point settings, select and set up the first point. Then you can adjust the robot pose and set up the second point. Adjust the robot pose and set up the third point. When it's done, you can confirm and adjust for the robot for the 4th point. Click Confirm after setting those 4 points. The robot will now calculate the parameters for this TCP automatically. In Manual Operation screen, change the TCP as the new TCP. Then, teach the robot pause. Let the robot rotate around the new TCP endpoint.
The third method, 6-point setting. This method is based on a 4th point method, adding 2 more points for the tool pause calculation, similar with the user coordinate system setting. The 4th point is the origin of the tool center position. The 5th point is the little upper toward the TCP Z axis. The 6th point is any point in the plane combined of Z or X. Okay, now let's have a look on the video of the 6-point settings. In Operation Setting, click Edit, select 6-point setting. Set up the previous 4 points as the same we saw with the 4-point settings. Then you can set up the 5th point. This point is in the Z axis of the tool. In the Z direction is along with the 4th point and the 5th point. Then you can set up the 6th point. This point is any point in the plane combined of Z or X. After the setup of all the 6 points, click Confirm. The software will calculate all the unknown parameters automatically. Then, in the manual operation page, we could teach the robot with this new TCP. Make the robot moving along with the negative direction of Z axis. Comparing with the 4-point setting, the software calculated the robot's pause automatically.
Let's go through the cautions for the tool setup. First, in case of absolute accuracy not required, we could create a TCP roughly instead, as long as it's easy for teach. Second, in case of exigent scenario, such as a collaboration with a 2D, 3D camera, or the robot must move in a perfect straight or circular path, we'll need to create a precise TCP. Third, during creating a TCP with the 4 points method, we need to ensure that the tool end is pointed to the top of a point from all angles. The result could be not accurate enough while the offset is just within 1 mm for one out of 4 points. Fourth, It would be difficult to create a precise TCP with a 4 points method if we don't have the correct tool and target, such as there is no pinpoint on a tool or it's not sharp enough. Fifth, regarding the judgment of the TCP accuracy, after creating the TCP, take a reference object with a pinpoint, let the pinpoint on TCP rotate around the object pinpoint by large margin, rotate plus or minus 180 degrees. Observe that if these two pinpoints are always attached during the posture change. 6. In case of the TCP is not accurate enough, manual compensation is provided. Method referred to the last page of this document. Consult JAKA technical support if necessary. Last one. If the user is familiar with a skilled operation, 5 minutes will be enough to create a precise TCP for one robot. Application with the TCP programming. The first set TCP instruction. This is for creating a new TCP. With clicking this instruction, you can directly input the TCP position and pose parameters. With the second set TCP instruction, we could select the end flange or the other 10 TCP created in settings. Relative linear motion with TCP. In the relative linear motion, we could select the reference coordinate system as the TCP wanted. By clicking the relative linear motion, you can access the window where you can select the coordinate system you want to use. Application. Pickup with a 2D vision. The first one is the original position of the product. The second one is the position moved. The second position is offset 100 mm each in X and Y direction from the first position. And the RZ rotation is 30 degrees. Robot programming. First, set the TCP as an end flange. Join move to the position which is 100 mm above the pickup point. Relative linear move downward 100 mm. Wait for 1 second. Move upward 100 mm. Relative linear move 100 mm in the X-axis direction. Turn the TCP 30 degrees in the Z directions. Then move downward 100 mm with a relative linear motion. Wait for 1 second. Move upward 100 mm. Change the end flange TCP to TCP1 and repeat this operation. In this application, programming the robot first, then use the end flange TCP and the new TCP for relative movement. Run the program. The position will be offset in the case of using the end flange TCP after linear and rotate motion. By using the new TCP, the robot will reach the position specified. Now, let's watch the video about this application. Part 3. Method for TCP calibration. First, set up the parameters of the TCP with the 3 method provides. There might be some slightly offset. Second, make the tool endpoints to a fixed sharp point. Adjust the robot pose to RX 180, RY 0. The end of the robot points to the ground with this pose. Let the robot tool end rotate in RZ direction with the world coordinate system. The Z parameters of tool will not affect the tool end point during rotation, means ignoring the effect of the tool Z parameter. Third, rotate the tool 180 degrees in RZ direction. There will be some offset between the tool end and the fixed pin point below. Check the X offset of the tool end in the end flange coordinate system. The offset is caused by the X parameters of the TCP. The compensation will be half of the X offset. The compensation shall be negative of the measured result, such as when the measured X offset is positive 2 mm in the end flange TCP comparing the origin before rotation. The compensation of X parameter should be 1 mm. Fourth, adjust the Y parameter with the same method for X compensation in step 3. Fifth, the step 3 and 4 can be repeated, depends on the results. Sixth, rotate the tool in a RZ direction after compensation. The offset will normally under 1 mm. Robot arm accuracy should be considered if excessive. Note that calibration method is effective with the TCP X and Y parameter only. Z and rotation excluded. That's all for the TCP setup. Thank you for watching.
I/O functions. This training will be divided in 4 parts. 1. Types of I/O. 2. I/O configuration. 3. Expand I/O. 4. NPN and PNP relay. The lecture time should be around 15 minutes and the objectives are the following. Know the pin definition of cabinet NT-I/O. Know the I/O extension methods. Be able to use functional I/O. Know the common sensor wiring methods. Be able to deal with the NPN signal. Let's start. Types of I/O. Firstly, robot I/O types 2.1 cabinet has 16 channels digital input, 16 channels digital output. All of them are PNP type. Analog signals are multiplexed and can be selected as analog output or input port. As shown in the figure, under the label of the cabinet, its 2.1 panel DO and DI each serve as 16 internal ports of the cabinet. Terminals P1 and P3 are digital input ports for connecting input signals such as sensors and switch buttons. DI refers to the dry node input button on the wiring diagram. Connect one end of the dry node to the positive power terminal and the other end to the DI input button. P2, P4 specially refer to digital output port for output of signal or control of solenoid valves, indicators, etc. DO refers to the wiring diagram connect the positive terminal of the load to the negative terminal of the DO load to 0 volt. P5 terminals can be configured with 2 analog ports for collecting analog signal or controlling devices. P6 high-speed input interface for acquisition of high-speed encoder. Minicab I/O pins define input-output interfaces that are multiplexed by power interfaces. 485 master port, 485 slave port. Minicab as a record reuse I/O can be flexibly configured as input or output interface but are NPN type. Minicab has no analog signal. As shown in the figure on the right, the total number of digital quantity interfaces on the minicab is 7, and TIO at the end of the robot end flange.
The TIO has two DI channels. Two DO channels are NPN type, and one is AI input TIO pin definition at the end of the robot. As shown in the table, pin 1 is 24 volt, pin 2 is DI1, pin 3 is DI2, pin 4 is DO1, pin 5 is DO2, pin 6 is AI plus, pin 7 is AI minus, and pin 8 is the ground. I/O configuration method. Digital input interface can monitor the digital input status in a control cabinet. Click the digital I/O signal to change the name, select function settings, select the desired function for the DI in function selection. Click OK. When the DI signal is triggered, the function is enabled. I/O in the electric control cabinet window is the physical I/O in the robot electric control cabinet. I/O signal in a Modbus window refers to the I/O signal that is read from the Modbus address table after Modbus communication with external devices. Modbus window displays the I/O signal of the robot as a slave station. As shown in the picture on the right, click I/O to select the corresponding function. The functions supported by DI signal are shown in a table on the right. When there is a signal input, the DI indicator light corresponding to the control cabinet panel will light up. Each DI function needs different trigger conditions to distinguish the rising edge low level and the high level fault clearing function. DI can only clear collision alarms, but other abnormal alarms cannot be cleared. Reduction mode is to slow down the robot. The reduction rate of the second is less than the first. Reduction multiplier setting methods. Edit reduction mode multiplier in security settings and protection system parameter setting. To edit the reduction mode multiplier, make DI signal exit reduction mode first. How to make through I/O an electrical trigger so the robot can run with the default program. First, enter the program setting interface. Select the corresponding program in the default programs. Set up the completion by checking the three options. The robot loads the default program. After that, as long as the DI electrical signal is configured, the robot will automatically power on and enable, and then automatically run the default program. Note that when the default program is set up and the control cabinet is restarted, the program will be started at 100% of the global speed. DO signal supports functions. As shown in the table on the right, note that when there is signal output, the corresponding DO indicator light on the cabinet panel will light on. The idle states refers to the states in which the robot does not run programs and has nothing to do with the robot is powered on or enabled. The error status is that the robot triggered the collision alarm. Static states refer to the robot being at rest, such as program pause, program not running, program end, waiting for signal input. The moving state is different from the static state. Indicate that the robot is currently moving as long as the robot is moving, whether manually controlled or automatically runs the program. The electric control cabinet is on power on states and has nothing else to do with the robot body states. The reduction states of the robot indicate whether the robot triggers the reduction mode. The safety position signal is the DO signal output when the robot is in the initial position. The initial attitude can be modified in the robot attitude. How to trigger the robot to return to the initial position through DI and then DO signal. First of all, in the security setting, robot pose can be edited on the robot pose interface. Then, select one DI in the DI interface and return to the initial pose function. Select the DO function on the DO interface and select the position safe function. When the robot is in the initial position, in the safe position is set, DO will output this signal. Note that this function can be enabled without connecting DI to the initial location. Please refer to the JAKA Hardware Introduction PowerPoint or JAKA manual. Analog input-output interface can monitor analog signals. Click the analog input signal to select the signal function. Click the function selection drop-down window, select the corresponding function and click Confirm to take effect. Currently, AI signals support the following function: voltage input, voltage output, current input and current output. In the analog signal interface, the analog signal in the Modbus window is the analog signal in the Modbus address table for Modbus communication between the robot and external devices. Analog signals at different positions in Modbus analog have different data types. Based on the data type, to select the analog signal type.
Expand the I/O configuration. When the number of physical I/O in the cabinet is insufficient, you can expand the I/O module. TCP or Modbus RTU can be established between the module and the control cabinet through Modbus. For detail about broken Modbus software, see Instruction to Modbus communication. There is a dynamic I/O configuration function in the I/O panel, so that the control cabinet can act as the Modbus master station. This function is located in the upper right corner of the I/O panel and has two states: running and editing. When you switch the editing mode, tap plus to configure the dynamic I/O. The configuration includes Modbus TCP and Modbus RTU. Modbus mode connects over Ethernet. RTU mode is connected through 485. Fill in the necessary information according to the blank step in the figure. Set the following parameters for Modbus RTU communication. The length verification mode must be the same as the slave node. After you click OK, the newly defined Modbus module and the usage of the NPN expansion card are displayed on the I/O monitoring screen. The NPN expansion board is an external expansion device added when the customer cannot use its own 16-channel I/O. The electrical attribute of the expansion board is the matching characteristics of the NPN robot. The first step is to connect power plus and power minus of the expansion I/O board to the 24-volt power supply. Connect the ports A and B to the 485A and 485B interfaces of the USB RS485 connection and use Modbus debugging software to configure parameters of the expansion I/O board. For details, please refer to the product manual. Start the Modbus Poll software, insert the USB to RS485 converter cable into the PC. Click the connection menu, enter the connection setting interface, and connect according to the initial settings of the board description document. The fourth step is to configure related parameters according to the actual workstation situation. Step 5. connect AB of the expansion I/O to 485A, 485B on the panel of the control cabinet. Step 6. Open a JAKA Zoo app to connect the robot. Click the lower triangle to enter the RTU control interface. Click the upper right corner to switch the operation to edit and click plus. Next, edit to enter the extending I/O editing interface. The 7th step, write the parameters of the expansion I/O board configured by Modbus POL software into the configuration information table. Click OK and switch the edit in the upper right corner to remote expansion board that can take effect immediately after running. 24 volt and 0 volt are connected with the V plus and V minus of the board respectively. Connect the laptop to the network port of the board. You are advised to fix the IP address of the laptop to 192.168.1.37. You are also advised to change the unit ID to 1 and the Modbus RTU communication parameters to 9600 baud rate. 4. Confirm that the parameters are correct. Click the lower right corners to save and then restart the board. Last step, fill in the parameters of the board in the dynamic I/O configuration interface of the JAKA app and run it. This is the minicab PNP expansion interface schematic diagram. You can also see on the table on the right the different signal and types for the minicab. For the minicab, RS485A and B are connected to the D plus and D minus of the I/O expansion board. 24 volt plus and ground connect to the board V plus and V minus respectively. NPN PNP relay. On the right, we can see the internal structure of a relay. The relay consists in 4 parts: coil, magnet, spring, and contact. The essence of relay is to use one circuit to control the on-off of another circuit. And the 2 circuits are generally isolated in this control process. The transfer contacts of a relay are 1 moving contact and 2 near contacts of the relay. The moving contact and the static contact 1 are in a closed state, which is called a normally closed contact. The moving contact is disconnected from the dynamic precession contact 2, which is called normally open contact. When the coil is energized, the moving contact is immediately disconnected from the feed contact 1, and the static contact 2 is closed to cut off the control line of the static control 1. And the control line of the static contact 2 is connected. When the coil loses power, the moving contact is reset. That is, the moving contact and the input contact 2 are reset and disconnected. And the static contact 1 is reset and closed, and the control line of the input and output point 2 is cut off, and the line of the static contact is connected. The diagram on the right is the physical picture of the combined and full relay. PA2 is the positive and negative pole of the coil respectively. When the contact of the coil is energized, the normal arm, the contact is disconnected, and the normally open contact closes the wiring diagram of the control cabinet. Coil positive terminal is connected to the output high level. Coil negative terminal is connected to low level COM command contact. Since CAB 2.1 is effective as a PNP input high frequency, COM terminal is connected to 24 volt high frequency. If NPM type is needed, COM terminal step frequency normally open contact is connected to the second and 8th as a signal input terminal.
When the coil is switched on, DR8 receives a signal. That is all for this course. Thank you for watching. Other functions in setting. This course will be divided in 5 parts: trajectory record, controller name and IP setting, import and export, fault diagnosis, security zone. The course duration is around 10 minutes and the main goals are the following: able to import and export programs and profiles, able to set up communication with external devices, be aware of trajectory record, the fault diagnosis, and set up the security zone. Trajectory record. The trajectory record provides the function to record the robot track in a certain time. Then click play the record with the track record instruction in program. Let's have a look at the video, see how to use this function. In the trajectory record of program setting, click the plus icon to start recording the motion. Then we could teach the robot via manual joystick or drag mode. Click stop to complete recording. In a trajectory record screen, we could edit the path file name. Then, in the programming control, add trajectory record instruction and select the path we just added. Run the program, the robot path we just dragged will be reproduced. Change robot IP and name. In the initial screen of setting system, we can change the robot name. Input in the rectangle the name you want to give to the robot and then click confirm. Change robot IP address. Enter the system setting page, edit the robot IP in the network setting. 2 modes are provided: auto-assigned IP and static IP. Regarding the version 2.1 controller, the IP of the LAN port at the front controller default IP is 10.5.5. something. External devices connected to this port shall be assigned in the range of 10.5.5.101 to 10.5.5.254. While the LAN port at the bottom of the controller default setting is DHCP, in case of a fixed IP is required, tick the option, use the following IP address, and input the new IP. Note that those 2 ports IP must be 2 different networks. Regarding the minicab controller, the LAN 2 port default setting is DHCP. And the LAN port at the front of the controller default IP is 10.5.5. something. The IP of external devices connected to this port shall be assigned in the range of 10.5.5.101 to 10.5.5.254. Import and export data. Open the system backup option in the system settings. Tick the profile types, click Export File button and select the destination for exporting. Click the Import File button, select the corresponding compressed file for importing. Let's go through the video of import and export profiles. In System Backup screen, we could select the profiles for exporting. Click the Export button, find the destination in local disk for exporting. In case of import, click the Import button at Local Compressed File, click Confirm. The profile will be then imported. Program File Import and Export. Click the folder icon in Programming Control page. The Export and Import button can be found on the top right of the pop-up window. Let's watch the video for exporting and importing program files. Click the folder buttons and then click the Export button. Select the program files you need to export. Click Confirm. Select the destination to export the program files. When you click on the Import button, you can select the local compressed file. Click Confirm to import the program files. The zip extension can be selected to open a program into the JAKA Zoo app. Fault diagnosis. In case of robot fault occurred, the controller will record the fault automatically and save it as a file name with the time occurred. In case of collecting the robot data during robot running, clicking the left button in the operation option, the controller will also record the operating data during normal running. Set for start fault diagnosis manually are below. 1. Enter the fault diagnosis screen under General Setting. 2. Click the Start Fault Diagnosis icon on the top right corner. Click Stop Fault Diagnosis icon to stop. After diagnosis reported generated, click the icon besides the file to report it. Let's have a look at the video of fault diagnosis. In this video, in the fault diagnosis page of operating setting, click the default diagnosis button to start and record for a period. Then click Stop to complete the diagnosis process. A file will be generated in the fault diagnosis page. Then you can click the export icon and select the local path for export. Security zone. Find the security zone option in safety setting. As the right side picture, there are 6 security planes can be set, from plane 1 to 6. Each plane is combined with 3 points. With setting the plane point 1 to 3, the plane is divided in 2 sides. And the security point will define each side is safe for operation. This course ends here. Thanks for watching. Maintenance interface operation. 1. Release brake manually. 2. Multi-turn value. 3. Joint calibration. This course will be around 5 minutes and the goals are the following. Able to release brake manually and drag the robot in an abnormal condition. Acknowledge the function of a multi-turn value and joint calibration option. Let's start. In case of the joints in error status such as a brake jam, display joint angle in abnormal during operation robot. Enter the maintenance interface for maintenance with the JAKA Zoo app. How to enter the maintenance interface? By clicking the JAKA logo 10 times continuously, the login window for maintenance will pop up. To enter it, the password is JAKA Amazing, all capitals. When to release the band type brake? In normal circumstances, the robot joints can be slightly moved due to the external force. But the joints might jam in case of a serious collision, causing robots not able to run properly. In this case, we shall identify the jam joint and release the brake to solve this issue. Caution for this operation: before releasing the brake, ensure the robot is fixed properly. After releasing the brake, the joint release will be loosened completely, and the end of the robot might fall down around its joint due to gravity. Steps for releasing the band type brake. First, disable the robot, but keep its power on. The tool head LED ring light remains in intermittent blue. Second, ensure the robot is fixed properly. Third, enter the release band type brake in the maintenance interface. Fourth, select the joint jammed. Fifth, click release band type brake. Sixth, push the robot to the proper position. Then click resume band type brake. Release the robot slowly. Eighth, push the robot again. Ensure the brake is resumed. Multi-turn value. This operation is usually not for customer. If it is required, it's only allowed to be carried out by or with the guidance from JAKA's technical staff. When the robot suddenly de-energized due to accidents such as a serious collision or trip, it might result in an encoder multi-turn value or lost turn value issue. After re-energize the robot, the angle reading of the joint is less or more than 360 degrees than the normal value. In this case, adjust the turn value for the abnormal joint in the maintenance interface. Step for edit turn value. 1. Disable the robot but keep it powered on. 2. Navigate to the multi-turn value option in the maintenance interface. Select the abnormal joint. Click the number of turns +1, -1 according to the current joint angle displayed to make it return to normal. Notice that the robot pause on manual operation screen shall be the same with the actual robot. Joint calibration. This operation is usually not for customer. If it is required, it's only allowed to be carried out by or with the guidance from a JAKA technical staff. In case of joint replacement due to joint malfunction, calibration is required for the new joint. As this calibration result will affect the absolute accuracy of the robot, usually it is not recommended to calibrate it by a customer only. Here are the steps for the joint calibration. 1. The joint which requires calibration to the 0 position with the teach pendant. As the pose in the right side picture, the X positive direction of the wall frame is along with the power cable connector or robot base, and the TIO connector as joint 6 is upturned. 2. Enter the maintenance interface, select the joint calibration option. Click the corresponding button, joint calibration is completed. This is the end of this lesson. Thank you for watching.
Hello and welcome. On this first video, Introduction of Motions, we will talk in details about the different types of motion of JAKA cobots. Let's start. Let's first have a look on the general content of this course. First we will talk about linear motion, then joint motion, relative linear motion, and we will end with circular motion. The lecture time should be around 16 minutes, and we have two objectives: understand the motion commands and know about the singularity. Let's start. First one, the linear motion instruction. First, we will have a look on a linear motion in a simulation software. We can see that the trajectory of linear motion is a straight line. This is the first feature of linear motion. Second, we record the linear motion of the robot and tool in a Cartesian coordinate. That is the values of x, y, z, rx, ry, rz. At last, the linear motion will involve an inverse solution calculation, so there will be singularities in linear motion. The JAKA robot has 3 singular points and position. The first one is the shoulder joint singular point. The intersection of the 5 and 6 axes of the joint lies in the plane formed by the 1 and 2 axes.
The second is the singular point of the elbow. The 2, 3 and 4 joints of the robot are coplanar. That is, robot big arm and forearm are almost collinear. The third singularity position is when the joints are parallel to the 4 or 6 joint. Now take another look at the programming instruction for linear motion. Click on the function to open an editing interface. In there, we can first modify a name of our point, that is a remark information of this point. Second, we can go to set the speed and acceleration. The recommended acceleration is below 1000 mm per square second. The third attribute is to stop or arc transition at this point. Fourth, the instruction skipping condition. When a state set by stop condition is made, our robot will skip this instruction. The fifth one is to edit a point of our machine movement. Click on editing interface and it will jump out of the picture on the right, which is interface for teaching the robot. After the teaching is completed, click OK and then return to our previous interface, click OK again. And then our motion instruction is edited. Now watch the actual linear motion. In our programming software, we can start to set the first point. This is our second point. And then we can teach the third position. We see that we have set 3 points in the program. And then the robot will add a loop. And the robot will walk a triangle between these 3 points. At this time, let's modify the second point. We will add an arc transition to the second point with an attribute of 50 mm. Save our program and then run it again to see the effect on the machine movement. Okay, we saw in the video that the robot did not accurately reach the position of the second point, but made a transition through an arc. We need to pay attention to some things when executing motion instruction. Because our linear motion records on Cartesian coordinates, when we modify our tool coordinate or system coordinate in the program, the point of the linear motion will also change accordingly. Then, the joint motion instructions. As previous, let's look the trajectory of the robot's hand into the simulation software. We can see in the video that when the robot moves through joints, the trajectory of the hand tool is an arc. This is the first characteristic of joint motion. Second, our joint motion records the angles of the 6 joints. Let's take a look at programming instruction for joint motion. As previous, we can see all the action we can do for joint motion. But different from linear motion, the speed and acceleration of joint motion refer to the joints movement. The recommended acceleration of a joint motion during programming is below 400 degrees per square second. Our joint motion uses 6 joints degree. So when you modify the user coordinate system or TCP in the program, the motion position will not be changed. For edit, it will be the same action as previous for linear motion. Let's take a look at the actual running effect of the joint motion in the program. After the teaching is completed, we can run our program. We will see that the robot make a move to the 4th point towards Biot in a joint motion. Relative linear motion. When you click on our relative linear motion, it will jump to this interface. As previous, you can set names for these positions. Next, there is the choice of reference coordinate system. Here we can choose the user coordinate system or the tool coordinate system. The choice of the reference system will determine the direction of our relative linear motion. Then you can also set the relative value of speed and acceleration, because the speed and acceleration of the motion are the same as our linear motion. As always, you can choose to stop at these points or add arc transmission. At last, you can enter the value of the linear motion where the robot will move accordingly to the current position. Okay, now let's take a look at the motion effect on relative linear motion. First of all, we need to set our initial position. Then edit the properties of our relative linear motion. Here, our second motion command is 300 mm in the y direction, and the third is 300 mm in the x direction. Then the fourth y direction is minus 300 mm. Here we choose our user coordinate system in the properties of our relative linear motion. So we did not set our coordinate system in our program. The default is to do a relative linear motion under a world coordinate system. The end of the robot is 300 by 300 square. At last, let's see the circular motion. First, click on the arc motion to start the arc motion editing interface. In this interface, we can set the speed and acceleration of our arc motion. The speed and acceleration here also refer to the TCP at our robot's end. Then the second one can be edited to choose to stop at this point or arc transition as we saw previously. Then the third is to set one of our passing point. That is to say the middle point of our arc movement and our end point. Click one of our icon 1 or 2 and then it will jump to our robot teaching interface. Let's try teaching our robot's position and then click OK to return to an interface of our arc motion editing. Fourth, the number of motion circle. If the number of motion circle remains 0, the robot will perform a 3 points motion, corresponds to a semicircle. In point 1 to let the robot perform a full circle motion. Look at the motion effect of our arc transition and its programming. First, you need to teach the starting point of the robot. It will be the first point of our arc motion and also the current position of the arc. Then you need to teach the point in the middle and the point at the end. For that, you need to click on 1 and 2. It will jump into the teaching robot interface. When it's done, we can run the program. We saw that our robot made a 3-point arc motion. Now let's modify our program and set a full circle motion. Now, let's change it to 2 circles.
So we saw that after 2 arc moves, there will be a pause on 1 second. Now let's modify the number of circles and put 0.25 a circle. The robot made a quarter of a circle. This concludes the content of this section. Thank you for attention. Welcome back. For this video, we will talk about control instruction for programming. This section of the course mainly explains the programming control instruction of the JAKA app. There are mainly the following part. 1. Coordinates and tool related instruction. 2. Load settings instruction. 3. Waiting instruction. 4. Cycle or loop instruction. 5. The main program call instruction. The duration of this course is about 10 minutes. The course objective is to understand the control instruction and be able to use them proficiently. 1. Coordinate system instructions. The first function is the instruction to modify the coordinate system in the program. There are 2 commands for setting TCP in the program. The first one can manually input the new TCP. The second one can select the TCP established in the settings, manually input the TCP and click the Set TCP icon to enter the tool coordinate system editing interface. In this coordinate system, you can manually input the parameters of the coordinate system and select the TCP command. Click the TCP drop-down list. You can select the end flange center in the list or the 10th TCP set in the settings. Create a tool coordinate system in a program or set the tool coordinate system established in a setting. After setting TCP, the position of the movement point in the Cartesian coordinate will change accordingly. Set the user coordinate system in the program. There are 2 types as the previous function. Manually enter the user coordinate and click to set it. The user coordinate system editing interface will pop up, where you can manually enter the user coordinate system parameters. Click the drop-down list to select the user coordinate system. You can select the world coordinates or the user coordinate system established in the settings. The movement point position of the coordinate will change accordingly. 2. Payload setting. Modify the load and center of mass in the program. This instruction can modify the end load and the center of mass during the running of the program. You can manually input the load and center of mass at the end attached to the robot, or you can drag inside a digital variable. Set application scenario for complex instructions. When the load changes during the running of our program, we need to use the instruction to set the load. When the load set during operation does not match the actual load, there may be vibrate or collision warning during operation. In real applications, if the load of the product itself is very small, for example only 100 or 200 grams, can be ignored. We cannot use the instruction to set the load. If the weight of the product itself is relatively heavy, for example 2 or 3 kilograms, when the product is clamped by the jaw in the program, the load of the mechanical end will undergo a large change. At this time, we need to use the load setting instruction to tell the robots that the end load has changed. When we put down the product, the load on our hand will become smaller at this time. So we also need to use the load setting instruction to tell the machine a current load and a position of the center of mass. 3. Waiting for instructions. Click on the control instruction bar, and you can see 2 waiting instructions as shown in a figure on the extended page. The first one is to wait for a specific time. After entering the waiting time, the program will continue to run after waiting for the input time during runtime instructions. The second is to wait for a specific condition. You can fill in a specific judgment condition in the check-in box.
When the instruction is executed, it will continue to wait in advance, and the program will continue to run until the condition is met. The usage method is as follows. First, you can wait for a specific digital input signal, and second, you can also wait for the logic judgment condition. 4. Introduction to loops and judgment instructions. The basic loop. The instruction is always looped, and the program will execute the command contained in the instruction loop. It will not end until the end of the loop instruction. Loop a specific number of times. You can either enter a number of times you want to repeat the loop, or use a variable for optimized programming instructions. If the conditions are met and the loop is executed, the program will judge after running the instruction. When the judgment condition in the space is met, the instruction contained in the loop will be executed. Until the condition is not met or the operation ends, the loop instruction will end the loop. End the loop. This function terminates the loop closest to the instruction when a specific condition is met. Generally, a judgment condition is added to the program, and the current loop is terminated immediately when the condition is satisfied. As shown in the example on the right, the action is executed in a loop. If the condition to the end loop is not satisfied, the action ABCD is executed in a loop. When the end loop condition is met, the action AB is executed, and then the current loop is ended. The program automatically terminates without subsequent instructions. Skip this cycle. Function, when a specific condition is made, terminates the loop closest to this instruction. Add a judgment condition before this instruction. And if the condition is satisfied, skip this loop and return to the beginning of the loop to continue executing the loop. As shown in the example on the right, the action ABCD is executed in a loop. If the condition of skipping this loop is established, the action AB is executed when the loop, and then the action CD is skipped. Judgment instructions. If is a true command. If the condition is satisfied, the content inside the command frame is executed. As shown in the command on the right, if the condition is satisfied, the action ABC is executed. If the condition is not established, only the action A is executed. If true, otherwise command. If the conditions are met, execute the upper half of the procedure within the framework. Otherwise, execute the lower half of the procedures. As shown in the example on the right, if the condition is satisfied, the action ABD is executed. If the condition is not satisfied, the action ACD is executed. 5. Call main program instruction. Click the drop-down list on this subcommand. We can see that we can select the program we have written in a drop-down list. Its function, when the program runs the instruction, it will jump from the current program to the selected main program and run from the very beginning of the main program. When the called main program ends, it will automatically return to the current main program. On this example shown on the right, the program executes action A, B, and then calls the instruction called by main program. After the main program calls the command, the action C, D will be executed. The all programs run the action in order A, B, E, F, C, D. This is the end of this lesson. Thank you for watching. This next course will be Introduction to I/O Instructions. The content of this class will be first introduction to output, input, then the use of digital signal and use of analog signal. The lecture is around 5 minutes and the main objectives are to understand I/O instructions and where analog signal is used. Here are the main I/O instructions you can find into JAKA programming interface. This is a summary of all functions can be used both for digital and analog signals. Digital signals can be operating by binary signal 1 and 0. Analog will be able to use number for instructions. We will enter more in details in the next slides. Set digital output. Control the tool at the end of the robot or a function plug on the controller. For example, a gripper which have a simple digital communication. Set digital output while robot moving. Same function as previous, but consider the robot movement. For example, the gripper can be opened during a movement of the robot and save some time during the operation. Wait until digital output to be on. Judgment instructions to set a wait while executing the program. Can be used as a switch to start a specific movement of the robot, for instance. Set analog output value. Ask the robot to set a value while running the program. This can measure degrees of joints or acquisition of tool end coordinates, for instance. For analog values in motion, it can be used for measurements of the speed. Digital input-output inside the calculation. The diamond-shaped instruction is meant to be used with a calculation condition. It can be used, for example, in the loops with judgment condition or true-false conditions. Get analog input-output value can be used to send the robot new information while running the program with analog signal. Can be position or specific tool using numerical values. The use of digital I/O function is as follows. You can change on drop-down list if we use a tool end plug or cabinet plug according to where our tool is plugged. Then you can choose which DO number you want to set, and finally is your operation requires to be on or off. On the lower section you can observe the main operation you can create with judgment instructions. The use of analog signal function is as previous. You can change on drop-down list if we use a tool end or cabinet plug according to where our tool is set. Then you can choose which DO number you want to set, and finally you can set the value you want for the operation. On the lower section you can observe the main operation you can create with the judgment instructions. Analog has two different channels, voltage type and current type. You can see on the right the voltage and current range for analog values. Analog can also be used with Modbus. That is all for I/O instructions. Thank you for attention.
Welcome back. For this class, we will talk about the variable. The content of this class will be the following. 1. Use of numerical variables. 2nd, use of array variables. 3rd, use of string variables. 4th, use of speed variables. And at last, use of positional variables. The lecture time will be around 10 minutes, and the objectives are following. Understand the different types of variable, understand the role of variables, and understand the user scenario of read-write methods of various variables. The concept of variable comes from mathematics, which is an abstract concept in computer language that can store calculation results or represents values. Variables can be accessed by variable names. In an instruction language, variables are usually mutable. Click Add Variables on the programming interface to add the following types of variables: system variable, number type, program variable, number array, string type, speed variable, and position variable. The system variable is the global variable, which can be used in different programs. After the program stops, the number of system variable will not be restored to the initial value. The program variables are, on the contrary, local variables, can only be used in a current program. The program variable will be restored to its original value after it stops. If you need to delete the added variable, you can click on the minus sign and the delete button will be displayed after the variable. Click the delete button to delete the existing variable. In addition, system variables can be added in our setting interface program settings. Currently, only numerical system variables are supported. Let's look at an example with a variable number. For this program, we will make a 3x3 palette counting variable, increase 1 each time. The start of this program specifies the initial feeding position, which can also be given by external device. If we use the system variables, we can change them directly into the settings. We set a variable number called num, and we will input inside the value 3. Then we have a repeat loop for the whole operation and a function of a palette. Inside this palette, we will have two linear motion, down and up, like to pick up a part. The initial position will be the position inside the variable. Here on the example will be 3. After making the up-down movement in the palette, the robot will set the numerical value to be +1. Variable equal variable +1. Then the instruction here will be ignore, because it's not greater than 9. Then the robot will make a loop and pick up the parts as long as we need to reach 9. When the numerical variable num is greater than 9, it will reset the variable to 1. And then it will start again the movement. Now let's have a look at a variable array example. The program uses array variable to hold Cartesian coordinate at the end of the robot. After, it uses numerical variables to hold a specific element of array. For this example, we'll consider an array in the program variable family, hold 6 subscripts. Each subscript corresponds to a position of the robot with a Cartesian coordinate. Subscript 0 corresponds to x, subscript 1 corresponds to y, subscript 3 corresponds to z, and the 3 last correspond to the rotation around x, y, and z axis. Now we will look on the program on the right. First, we start to create 3 variables. One array called current position, and 2 numerical values called x and y. The first line of the program will ask the robot to input inside our array called current position the localization of the end tool center location. Then the robot will input inside x and y using subscript 0 and 1 the current position of x and y. After, we will see 3 conditions. If x is greater than 0 and y greater than 100, the robot will move to the A position. If the x is greater than 0 and the y less than 0, the robot will move to the B position. Both are using a joint motion. The last condition is x is less than 0 and y greater than 200. Then the elements inside the array for the z value will be set at 200. Then the robot will move to the modified value. It is possible to input inside the linear motion the localization inside the array. It's like a coordinate for a point. Then it will be the same for the y value and x value. This condition allows the robots to move each position by each position. After the program is finished, the robot will return to the initial position. Now we are going to talk about the function access subscript. The access subscript function is a way to read the information inside the array. For example, in this program, we use this open socket program to ask the robot to read inside the subscript number 3 and send us what's inside. For example, the name of this array is 2 with these current values inside. All the values are separated by a comma. By using the program of accessing the subscript number 3, we see that the final result will be 85. Because indeed,
Subscript 0, 1, 2, 3 is 85. For information, the subscript 0 here corresponds to 256 and the last subscript number 5 corresponds to the 96. Remember that we always start the subscript with 0 and finish with 5. For the next function, it will allow us also to read inside the array. The only difference is we can choose where to start and where to end. For the following program, we wrote a communication protocol and asked the robots to send us what's inside the array. We want to cover all the elements inside the array, so we choose the start at 0 and the end at 5. The step value of 2 will ask the robot to read every 2 numbers inside the array. With such program, we can see that the result will be 256, 10, and 0. If we watch the result, it is correct. If you want the robot to give us every element inside the array, we should choose a step value of 1. The next function will be set array elements. With this command, we can modify the element inside the array. In an example here, we want to change the subscript number 3 and replace it with the value 888. If you remember the element inside the array, the subscript number 3 will be 10. After running the program, we can see that the element inside the array, subscript number 3, have been replaced with 888. The string. The variable string allows us to put not only numbers but words inside the variable. When you use a communication software, if you want to put even numbers into a variable, you need to use a string. If you want to convert these numbers into a position, we need to use this function to convert the string into array. Let's have an example. Here, we start to set an initial position for the robot. Then, we establish the communication sockets and wait for 1 second. After, we ask the robot to put inside the string what we write in the communication software. Then, we establish a string with no value inside. The same for the array. We don't need to put initial values inside. Then, after the robot moved, we ask him to send us OK in the communication software. Here, we notify the robot that we will separate our position by a comma. After, we set the IP address of the robot and connect. We can run the program. When the program is launched, we just need to send the robot the new coordinate. Here will be the Z position. So the robot will simply move along the Z axis. We see the behavior of the robot. He moves and then sends OK. We don't need to relaunch the program every time. The program is optimized to be used without touching it. The variable velocity can cover the speed set in the motion instruction and run accordingly to the global speed setting. The global velocity will overwrite the speed previously entered in the joint motion. Close the global speed command will cancel the motion speed override function. The next motion command according to the speed set in the motion command operation. For the example on the right, here, the joint motion 1 and 2 will be executed with the global velocity named speed. The speed entered in the joint motion 1 and 2 previously doesn't matter. After the join motion 3 and 4 will be executed with speed 2. After closing the global velocity, the speed entered previously into join motion 5 and 6 will be executed normally. Variable position. The variable position supports manual input of joint or Cartesian coordinates. Click Edit to teach robot coordinates to automatically obtain the current coordinates. Then you can rename your variable, click on every coordinates to manually input yourself. You can also choose user coordinate and tool coordinate system. When you're done, you can click Determine and the robot will remember the position. In a program, you can just select your joint or linear motion and then slip the variable inside the position. When you execute the program, the robot will move to the position inside the variable. Variable position is useful for frequently using points. For example, pick and place or palletizing. This is it for the variables. Thank you for watching.
Calculation instruction. Introduction to calculation instructions. This section of the course mainly explains the programming calculation instruction of the JAKA app. It contains the following parts. 1. Calculator instruction. 2. Mathematical function calculation instruction. 3. Comparison and logic operation instruction. 4. Plan transformation related instructions. 5. Direct and inverse solution instructions. This lesson lasts about 20 minutes and the core objectives are 1. Proficiency in mathematical calculations and logical calculation instructions. 2. Briefly understand the related instruction of the plan transformation. First, look at the calculation operator instructions. Click the drop-down list in the middle of the calculation operator to select addition, subtraction, multiplication, and division operation. Let's look at an example of the application of the calculator. First, open the socket connection. Set the program variable a, b to 3 and 2 respectively. And then use the socket to send two variables to add, subtract, multiply, and divide to obtain a result of exponentiation. The following figures show the network debugging assistant server receiving results. The second is the mathematical function calculation instruction. Click the drop-down list of the instruction to select the corresponding mathematical function. Look at the example on the right. By sending the calculation result of the math function, the function can be cosinus, sinus, tangent, arcsinus, arccosinus, arctangent, natural exponent, natural logarithm, rounding up, rounding down, absolute value, square root. The following figures show the result of the function calculation received by the socket communication. Comparison operators. Click the drop-down list of the comparison operators. You can select less than, greater than, equal to, not equal to. Then less than or equal to, greater than or equal to, and the instruction returns logical true when the conditions are met. Logical operators like AND operations means like both are true and the result is true. Logical OR operator if one of the two is true. XOR operation, the result is true when the two are different. Logical negation operator, the result is true when the condition is false. Logic operations can be nested. Position addition command. Position variable or teaching point can be dragged in, and the command return value is a calculation result. Look at the program example on the right. First, open the socket communication. The socket sends the result of the position calculation, moves linearly to the position variable P1.
and then makes a relative linear movement under the user coordinate system. The moving parameter is the unknown variable P2. After the movement is completed, the socket sends the current flange center of the robot position coordinates. Then, move linearly to point P1 and move linearly to the calculated result. The socket sends the position of the flange center again. The following figures show the result of the socket 3 times. We will see that the results of the socket 3 times are the same. The understanding of the position addition command is shown in a figure on the right. P1 is the Cartesian coordinate of the tool in a user coordinate system. P2 is the position to be added, and the parameters are 6 tens. Its function is to first move P1 around the user coordinate system x, y, z, shift 10 mm in each direction, and then rotate P1 around the positive x-axis of the user coordinate by 10 degrees. Then rotate P1 around the positive direction of the y-axis in the user coordinate system by 10 degrees. Finally, turn P1 around the z-axis in the user coordinate system by 10 degrees. The relative linear motion in the user coordinate system is the function, and the transformed pose is the result of the position addition. Position subtraction instruction. Drag in a position variable or teaching point. The return value of the instruction is the calculation result. Position is calculated in Cartesian coordinates. Look at the example on the right. Open the socket connection. The socket sends the result of the position subtraction. The robot is applied to the point P1 in a straight line. Under the user coordinate system, the relative linear motion Rz is minus 10 degrees. The relative linear motion Ry is minus 10 degrees. And the relative linear motion is Rx minus 10 degrees. Relative linear motion x, y, z each translates minus 10 millimeters. After the movement is in place, the socket sends the position coordinates of the robot's flange and center, which is applied to the point P1 in a straight line. The linear movement is the result of the position subtraction. The socket sends the position coordinates of the center of the robot flange. And we will see that the result of the 3 socket sendings are also the same. The understanding of the position subtraction command is shown in a figure on the right. P1 is the Cartesian coordinate of the tool in the user coordinate system. P2 is the position to be subtracted, and the value is 6 tens. Its function is to first rotate P1 around the z-axis of the user coordinate system by minus 10 degrees, then rotate P1 around the user's y-axis by 10 degrees, and then rotate P1 around the user coordinate system x by minus 10 degrees. Finally, P1 is shifted by minus 10 millimeters along the direction of the user coordinate system x, y, z. And its change its order is just the opposite of the order position addition. The changed pose is the result of the position subtraction. Position change instruction. You can drag in position variable or teaching points. The return value of the instruction is the calculation result, and the position calculation is Cartesian coordinates. Look at the example on the right. First, open the socket communication. It sends the result of the position transformation. The robot moves linearly to the position of the variable P1. Then the robot makes a relative linear motion under the tool's coordinate system. The motion parameter is P2. After the robot moves in place, the socket sends the coordinates of the center position of the flange, and the robot moves linearly to the position of variable P1. The robot moves linearly to the result of the position transformation. After the robot moves in place, the socket sends the coordinates of the center position of the end flange of the robot. Here, we can see that the socket received the three same results. P1 is the Cartesian coordinate of the tool in the user coordinate system. P2 is the 6 parameters to be transformed. Its function is to first translate P1 around the tool coordinate system direction XYZ by 10 mm. Then rotate PE around the Z axis of the tool coordinate system by 10 degrees. Then rotate P1 around the Y axis of the tool coordinate system by 10 degrees. P1 is the Cartesian coordinate of the tool in the user coordinate system, and P2 is the 6 parameters to be transformed. Its function is to first translate P1 around the tool coordinate system direction X, Y, Z by 10 mm. Then rotate P1 around the Z axis of the tool coordinate system by 10 degrees. Then rotate P1 around the Y axis of the tool coordinate by 10 degrees. Finally, P1 rotates 10 degrees around the X axis of the tool coordinate system, and the changed position is the result of the position transformation. It is equivalent to the relative linear movement under the tool as we advance. Let's look at the comparison of two functions. One is the position transformation instruction and the other is the position addition instruction. Both of these instructions return a Cartesian coordinates of the position in the user coordinate system. Two physical meanings. The position transformation is equivalent to the target point in the tool coordinate system. The dynamic coordinate system rotation sequence is Z, Y, X. And the translation rotation transformation is performed. The position addition target point is below the user coordinate system, and the static coordinate system rotation sequence is X, Y, Z. The rotation transformation is equivalent to a relative linear movement under the tool coordinate system, and the position addition is equivalent to a relative linear movement under the user coordinate system. Position calculation inverse transformation. The usage is to drag in position variables or teaching points, and the return value of the instruction is the calculation results. See example on the right. Set the user coordinate system to open the socket communication, and it will send the results of the P2 position inverse transformation. And the robot moves straight to P0. The robot moves in the relative linear motion under the tool coordinate system, respectively rotates negative 10 degrees around X, then rotates negative 10 degrees around the Y axis, then rotates negative 10 degrees around the Z axis, and finally translate negative 10 millimeters in each X, Y, Z directions. After the robot moves in place, the socket sends the coordinates of the center position of the end flange, and the robot moves to the result position of the inverse transformation of variable P2 in a linear motion. After the movement is in place, the socket sends the coordinate of center position of the flange of the robot. Have a look. The data received by the TCP assistant server 3 times is the same. An understanding of the inverse transformation instructions is as shown in the example on the right. P2 is the Cartesian coordinate of the tool in the user coordinate system. Its coordinates are 6 tens. P0 is the 0 position. Its coordinates are 6 zeros. And its function is to first move P0 around the tool coordinate series, rotates the x-axis by minus 10 degrees, then rotates P0 around the y-axis of the tool coordinate system by minus 10 degrees. Then rotates P0 around the z-axis of the tool coordinate system by minus 10 degrees, and finally move P0 along the x, y, z of the tool coordinate system. When the direction is shifted by minus 10 millimeters, the posture after the change is the result of the inverse change, and the changed order is the opposite of the changing position. Calculate position distance command. Look at the example on the right to open the socket connection. It will send the result of calculating the position distance P1, P2 and send the sum of the squares of the x, y, z difference between the two positions P1 and P2. And then open the result of the roots sign. The result received at the socket is 173.205. The result received is twice the same. Calculate position distance command understanding. Return position variable P1 and P2 position parameter x, y, z different of the square sum and then open the root sign, that is the distance between P1 and P2 in the space position. Calculation instruction. Interpolation points. See the example on the right. Set the program variable count to 1. Open the socket connection, loop 5 times. The starting position of the palette movement is 1, and the palette movement is one-dimensional and has 5 points in total. The 2 points of the palette are respectively P1 and P2. After the palette is in place, the center position of the flange at the front end of the socket sends the coordinates. The robot moves to the position of the interpolation point P1, P2 in a straight line. After the movement is in place, the socket sends the coordinates of the center position of the end flange. After the movement is completed, the count variable is increased by 1 and the cycle moves 5 times. The following figure shows a result of 5 palette movements and 5 interpolation point calculations. Understanding of the interpolation point instruction. Calculate the position of P1 and P2, that is the poster accordingly to the proportional difference. Refer to the palette instruction. The palette in the right picture is a one-dimensional palette with a total of 5 points. The 2 points of the palette are P1 and P2. The position of the palette movement is consistent with the result of the position calculated by the interpolation point. Plane transformation instruction. X, Y plane transformation. See the example on the right. Open the second connection. It will send the plane transformation result. The robot moves in a straight line to the P1 position coordinate. The robot moves in a relatively straight line under the user coordinate system. The parameters are x, y, rz respectively 10. After the movement is in place, the socket sends the end of the robot coordinates. The robot moves linearly to the result position of the plane transformation. After the movement is in place, the socket sends the coordinates of the center flange position of the robot's end. We can see that the result of the 3 receptions are the same. The understanding of the plane transformation command is as shown on the example on the right. P1 is the Cartesian coordinate of the tool in the user coordinate system. Its function is to first translate P1 along the user coordinate system, x, y directly by 10 mm, and then move P1 around the user coordinate system. The z-axis rotates 10 degrees and the change position is the result of the plane transformation. Plane transformation y, z can be used to drag in position variable or teaching points. And the command returns value is the calculation result. In the example on the right, the socket connection is opened. The socket sends the plane transformation result. The robot moves linearly to the position P1. And then it moves in a relative linear motion under the user coordinate system. The parameters are y, z, and r-axis respectively. And the socket sends the end of the robot after the movement is in place. The coordinates of the center flange position, the robot moves linearly to the result position after the plane transformation. Then the socket sends the robot end flange center position after the movement is in place. The following picture shows the socket received in a result. We will see that the data received 3 times is the same. An understanding of the plane transformation command, as shown in the example on the right, P1 is the Cartesian coordinate of the tool in a user coordinate system. Its function is to first translate P1 by 10 mm along the YZ direction of the user coordinate system, and then move P1 around the x-axis of the user coordinate system, rotates 10 degrees, and the changed position is the result of the plane transformation. Plane transformation ZX. See the example on the right. The socket sends the result of the plane transformation. The robot moves linearly to the P1 position and the robot is below the user coordinate. Make a relative linear motion. The parameters are Z, X, Ly, 10 each. After the motion is in place, the socket sends the coordinate of the center position of the end flange of the robot. Then the robot moves in a linear motion to the result position of the plane transformation. After the robot is in place, the socket sends the coordinates of the center position of the flange. The following figures show a result received by the socket. We can see that the result is the same 3 times. The interpolation of a plane change destination is shown in the example on the right. P1 is the Cartesian coordinate of the tool in user coordinates. Its function is to translate P1 along the X and Z direction of the user coordinate system by 10 mm. And then move P1 around the user coordinates. The y-axis of the system is rotated by 10 degrees and the changed position is the result of the plane transformation. Kinematics inverse solution instruction. Calculate the input Cartesian space position according to the selected reference angle value and the joint space coordinate corresponding to each other in the same solution space. We manually enter the Cartesian space position in P1 and manually enter the joint space position in P2, which is a position of our reference point. The socket sends the result of the inverse solution. The parameters of the inverse solution are P variables. The reference point is P2. Lift the robot to the position P1 in a straight line. After the movement is in place, the socket sends the current joint angle value and the robot joint moves to the result position of the inverse solution. After the movement is in place, the socket sends the angle values of the current 6 joint angle of the robot. The following figures show a result received by the socket, and the result is the same the 3 times. The meaning of the kinematics positive solution instruction is to calculate the position of the Cartesian space where the input joint angle is located. In the position variable P1, manually input the joint angle coordinates. The socket sends the result of the correct solution. Before the joint is moved to the position of P1, the socket sends the coordinate of the center position of the robot's end flange. The robot moves to the result of the positive solution in a linear motion. After the movement is in place, the socket sends the coordinate of the center position of the end flange of the robot. The following figures show the 3 results received by the socket. This is the end of this training. Thank you for attention. 3. Fill and use subprogram. The course duration will be around 5 minutes and there will be 2 objectives. 1. Add and use subroutines, and 2. Debug the subroutine separately. Let's start. A subroutine or subprogram is to form a sequence of instruction into a relatively independent program segment. When this program segment is added into the program will run the sequence of instruction in this program segment. To add the subroutine, click on the left tab called Subprogram, then you can click on the plus button on the top left of the page. To delete a subroutine, you can click on the minus button next to the plus button on the top left of the subprogram tab. Then
a little bin will pop up and you can click on it to permanently delete the subprogram. Subroutine programming is the same as the main programming. Add subroutines can make the program look more concise, easy to read, and gives a better understanding of the program. The name of the subroutine itself also has a function of annotations. Subroutine can be debugged separately, convenient debugging programming. On the example on the right, we can see that the different subprograms have different names which correspond to one function of the program. You can see that the green instruction makes the program more clear, and if you click on the subprogram, you can see what's actually inside the subprogram. Now, let's have a look on the video to how to fill into subprogram and how to use it in the main program. So first, select the elements you want to copy inside your subprogram. Then, you can go on the subprogram tab and create a new subprogram. Then you can just copy set, and the copied element will appear into the subprogram. Then you can, for example, rename it. Here in the example we can rename subprogram. Then save it. When it's done, the subprogram will appear on a list of subprograms. You can delete actually what was inside the subprogram and replace it on the main program. That is all for this lesson. Thank you for watching.
Character instruction. First, the string concatenation. Second, the string comparison. Third, use of format, output string. And finally, part 4, how to exchange between array and string. The time of this video will be around 10 minutes, and the main course objective is to understand how the character instruction work with socket communication. The string concatenation. The principle is to splicing two strings as one. Click this command to edit the number of spliced strings you want to add, from 1 to 8 strings. Then you can drag in variable or input strings directly inside the command. It can return the spliced string, and the return value is a string variable type. Look at the example on the right. We have 3 variables, A, B, and C. We want the communication device to send us 3 lines with each line containing 1 variable. So we put 6 strings into this function and input A equals to variable A, then back to the line B equal to variable B, and then back to the next line and C equal variable C. We can see on the result value the corresponding results of the programming. String or array length. This function basically calculates the length of the variable. You can drag inside the variable and the communication device will tell you how many entries inside this variable. Look at the example on the right. We have the first variable named B with the word hello inside. Then we have the variable C which is an array with the 6 numbers inside. Then we input inside the function A, B, C. As you can see, the result on the communication device, it gives us the length of the string by the word hello, which is 5 letters. Then it gives you the numbers inside the array, which is 6, and then the number of letters in the string A, B, C, which is 3. String comparison. The string comparison compares the value of the 2 strings according to the ASCII code. Drag in the variables to compare it. If string 1 equals string 2, returns 0. If string 1 inferior at string 2 returns a negative value. And if string 1 is superior at string 2 return a positive value. On the example on the right, we are going to compare two strings, string 1 and string 2. Both of the variables have the same number, 1. So here the instruction is making a comparison between string 1 and string 2 and the values return 0. This instruction can be useful, for example, login or password. If you set a if condition with the string comparison equal to 0, means that the password is correct. If it's not equal to 0, means the password entered is wrong. Formatted output string. The formatted output string specifies data as a string in a specified format. As always, click this command to edit the number of formatted data you want, from 1 to 8. Then you can input the required array separator and drag in the variables. You can also input values. The result of this command will be a string variable type. On the example on the right, you can see that the robot will put inside the variable pos L the position of the flange center pose, and in pos G the variable of the current joint position. Then we use the format output string to give us the position of the end flange and the joint. But in order to be clear, we can input inside which correspond to which value. At the end, on the result window, we can see that the position of the end flange and the position of the joint are clear. Enter a formatting string. Matches a string in a certain format and enters the matching data into specified variables. As always, click this instruction to edit it, and then you can drag in variables or directly input the values inside the holes. Look the example on the right. We have one string containing end load is 1, 2, 3, 4, 5, 6, and then we create an array called pos for position, where we can input inside the 1, 2, 3, 4, 5, 6. The instruction input format strings tells the robot to separate end load is and the 6 numbers. In this case, the robot will separate end load is and put the rest into a variable. Here, the variable is array. As you can see on the result, the robot will keep only 1, 2, 3, 4, 5, 6 containing inside the array. This instruction can be useful if, for example, you use a 2D camera and the camera sends you the data, the coordinates of the parts into a strings. Then you can use this instruction to cut the strings and put inside the variable the desired positions. Convert array into a string. This instruction simply converts the array into a certain format of a string variable. To do so, just input inside the instruction the array you want to convert, and then input the separator you want. For example, here we have an array containing the numbers 1, 2, 3, 4, 5, 6, and we want to turn it into a string. So we input the variable inside the instruction with A for separator. And we can see the result is now a string with 1, 2, 3, 4, 5, 6 separated with an A. Convert string to array. The action is simply to turn a format string to an array variable. Just dragging the string you want to convert and a separator for the array. On the example on the right, we want to convert the string 1, 2, 3, 4, 5, 6 to a classical array variable format is 1, 2, 3, 4, 5, 6 separated with the commas. So here we have a string with 1, 2, 3, 4, 5 inside, and we want to use the comma separator for the transformation. And the return value is 1, 2, 3, 4, 5, 6 separated with commas. That is all for this video. Thank you for watching. Introduction of palette instruction. The course will be divided in two parts. The first one, Introduction of palette instruction. The second one, Application of palette instruction. The lecture time will be around 10 minutes and there is two main goals. Able to use the palette instruction in actual application and be familiar with the function of a system variable in a palette application. Let's start. By clicking the palette instruction, the setup page will be displayed. In this page, we could select the palette type as 1 dimension, 2 dimension, and 3 dimension type. We could also set the count of the palette in row and columns. Then we have the points to teach the path. On the right, we can also see the figure for the points order in path. You need to set the point, for example here in 2 dimension, from 1 to 4, following the points in other paths on the figure on the right. Palette waypoint. User could add the waypoint for the palette. Notice the order for waypoint teaching. The definition of waypoint is the end position for robot after arriving each palette. How to use the waypoint? Add and click the palette waypoint instruction. We can rename the waypoint, set up the speed, the acceleration. We could also select stop at this point or the arc transition motion. This instruction is only valid inside the palette instruction. Notice that the palette waypoint is relative to the robot pose at the first position palette. To teach this waypoint, move the robot at the first position palette, then adjust the height or pose. Usually, the robot pose remains the same. This example shows the robot end moving in a 3x3 square palette with a pickup action. On the right side program, the program keeps looping from the palette initial position 1. Including 2 waypoints movement, the robot will move up 50 mm and move down 50 mm when reaching each palette. Edit the palette instruction, select 2 dimension type, the count of row and columns are both 3. Then, teach the 4 points of the 4 positions of the palette. Now let's have a look on the video of the palette motion. First, we need to edit and teach the 4 positions of the palette. Then we could set up the waypoints of the palette. When teaching the waypoints, normally we'll need to move the robot to the first palette position. Then we can run the program. We could see that the tool end is palletizing with a 3x3 pallets. Some more points about the palette motion. 1. The palette position and waypoints are Cartesian coordinate. Be careful to correct world and the tool coordinate while teaching. Second, the robot will move to the first point in case of starting the count exceeds the total count of the palette. Third, the waypoint is usually above the pallet, with adding waypoint to let the robot move downward. 4. The pallet waypoint is relative to the robot pose at the first position. To teach this waypoint, the robot must be at the first position pallet. Then adjust the aids or pose. Usually the robot pose remains the same. And fifth, waypoints could be replaced with a relative linear motions. Advanced example by using a system variable. To resume pallet instruction from the pallet position where the program stops, in case of simply stop command or collision, for example. At the right side program, we added a system variable for current pallet count. When the robot completes each pallet, add 1 to the system variable. Then check if this variable is bigger than 9 or not, which is the total count of the pallet. Then reset this variable to 1. In case of the program stop, the variable will retain and the robot will start from this current count for palletizing. As the system variable will retain after power of the program stop, it will add 1 after each pallet and reset to 1 when it exceeds the total count of the pallet. That is all for this course. Thank you for watching. Introduction of socket communication. This course about socket communication will be divided in 4 parts. 1. Introduction of socket. 2. Socket instruction. 3. Application of socket programming. 4. Socket debug tool. The course will be around 10 minutes and there will be 2 main goals. Be aware of sockets and programming. Be familiar with the socket debug tools. 1. Introduction of socket communication. What is a socket? Network socket is an inter-process communication protocol provided by the operating system. In the communication between 2 networks, the socket is an endpoint for each network. During communication, the application in one network stores the information in its host socket and sends it to the application in the other network via network transmission media. So those applications could exchange data via sockets. The socket expression is a decimal IP address with a port number with dot or comma to break it. For the socket application scenarios, in case of vision control or upper computer control requirement for customer, socket communication can be used for those scenarios. JAKA robot is a socket client in the applications. 2. Socket instruction. Open socket. Create a TCP client and connect with the TCP server. Select the ID from the specified socket, enter the TCP server IP and the port number when running the instruction. The TCP client will establish connection with the TCP server. Open socket and return the result. Create a TCP client and connect with TCP server. Return the connection result. Select the ID for the specified socket, enter the TCP server IP and port number. When running the instruction, the TCP client will establish connection with the TCP server. The return result will be greater than 0 if the connection succeeded, while it will be -1 if failed. Close socket. You can just close the socket connection. Select the ID of the specified socket when running the instruction. The socket connection will be closed. On the example on the right, we can see that the robot is opening socket connection with the socket number 1. Then set the program variable to -1. Then the if condition, if the program variable is less than 0, repeat the loop. Then the program will put inside the socket result variable the result inside the socket number 2. Wait 1 second and close both socket 1 and 2. Send data via socket. Send data to the TCP server from the robot controller via socket communication. Select the ID for the specified socket, enter the TCP server IP and port number. Drag the variable or input value inside. When running this instruction, the TCP server will receive the data. Note that the number, string and array variable are supported, not requiring special format, but Unicode characters are not supported. Send data via socket and return result. Send data to the TCP server from the robot controller via socket communication and return the sending result. Select the ID for the specified socket, enter the TCP server IP and port number. Again, drag the variable or input a value, and running this instruction, the TCP server will receive the data. This instruction will return the sending result. In case of sending succeeded, the result will be the length of the data, while it will be -1 if it failed. On the example on the right, we open the socket communication and then ask the robot to send us A with the result of the variable A, B and the result of variable B, and C and the result of variable C. On the network assistant, we can see the result with the content of every variables. Receive variable via socket. Definition: wait for a certain amount of seconds until receiving the variable. The robot controller will send the requested variable name, then start waiting for receiving the data. Select the ID for the specified socket, drag the variable into this instruction. In case of the controller doesn't receive the variable after a certain amount of seconds, the program will continue the next instruction. The robot will always wait until receiving the data if the waiting time is 0 seconds. Variable name with a Unicode character is not supported. We connect with the socket server, receive the variable and enter the data received. On the example here, after opening the socket communication on channel 1, the robot will ask us to receive the content of the variable A. Here on the send data, we can input the content, what we want to put inside the variable. For example, here 111, and then the robot will send us back the result of this variable. The same for the string for variable B and the array for variable C. Receiving array data with a specified length via socket. Wait for a certain amount of seconds until receiving the array data with the length of the specified length. The controller will send get string request and start waiting for receiving. Select the ID for the specified socket. In case of the controller doesn't receive the variable after a certain amount of seconds, the program will continue to the next instruction. And as always, the robot will wait until receiving the data if the waiting time is 0 seconds. If receiving failure or overrun, empty array will be returned, while the result will be stored in the array if succeeded. On the example on the right, we connect with the socket server, receiving array and return the result. So after opening the socket communication, we ask the robot to put inside the variable C the sent data with the array length of 6. So if we put an array with the 6 data inside, the robot will send us the 6 data of the array. Receive data via socket. The controller will wait for receiving the data for a certain amount of seconds. No extra data will be sent from the controller before start waiting. Select the ID for the specified socket. In case of the controller doesn't receive the variable after a certain amount of seconds, the programming will continue to the next instruction. On the example on the right, we connect with the socket server, receive the data and return the result. So we open the socket communication, then we input inside the variable B the data sent via the network assistant. and then the robot will send us back the content of this variable. Application of socket communication. Connect with the socket server, create string variable for receiving data from the server, then convert the string variable to array. With the format string instruction, the robot will make then a linear move to this array specified in Cartesian coordinate and send the string OK to the server after arriving to the position. Let's watch a video about the application. We are sending coordinates now with the network assistant. When the robot is receiving this data, it's making a move and sending OK. We can try to change the coordinates and the robot will always make a move and then send OK. Socket debug tools. Three options are provided by Hercules: TCP client, TCP server, and UDP. JAKA robot controller can be used as a socket client. Select TCP server options in Hercules. The IP address will follow the IP assigned to the PC network adapter in the app programming interface. The IP address of open socket instruction shall be the same as the PC network adapter. This port number is from the open socket instruction connection. Note that during the socket communication, the external device such as a PC and the robot controller shall be in the same network. In case of communication failure, turn off the network firewall in a PC. This course ends here. Thank you for watching. Introduction of Modbus communication. This course will be divided in 4 parts. 1. Introduction of Modbus communication. 2. Modbus TCP. 3. Modbus RTU. And 4. Modbus slave address table. The lecture time will be around 20 minutes and there is 2 main goals. Familiar with the Modbus and the content of address table as a Modbus slave, and be able to use the Modbus debug tool. Let's start. 1. Introduction of Modbus communication. Modbus is a serial communication protocol developed for PLC application. Based on this protocol, the controller could communicate with each other or communicate with other devices via network such as Ethernet. The Modbus protocol is a master and slave communication technology. The device requesting data is called Modbus master, while the device which providing data is called Modbus slave. In a standard Modbus network, there is one master and 247 slaves allowed. Each slave will have a unique address. The master is also able to write data into slaves. Modbus is an open protocol, which is free of charge. Currently, Modbus has become a standard protocol of the industrial communication, and it is most common communication method between industrial devices. Usually, Modbus is used to transmit data or signals from instruments and control devices to the main controller or data collecting system, such as measuring temperature or humidity and send it to computers. Depends on the Modbus protocol version, it could support both serial communication, Modbus RTU and Modbus ASCII, and Ethernet communication for the Modbus TCP. JAKA robot is compatible with Modbus RTU and Modbus TCP. How to use Modbus? In the Modbus serial communication, the simplest setup is that connecting the serial ports on those 2 devices, master and slave, with a serial communication cable. The data will be sent as 1 or 0, so called as bits. Each bit will send a volt as voltage. 0 stands for the positive voltage, 1 stands for negative voltage. The bits sending process is very fast. Typical speed baud rate is 9600 bits seconds. How is the data stored in Modbus? The data are stored in 4 different tables of the slave device. 2 of them are for coils and the other are 2 for registers. Both coils and registers include a readable table and read-write table. Each table includes 9,999 cells. Each coil is assigned as 1 bit in the address of 0000 to 270E, while each register is 1 word, 16 bits for 2 bytes, and assigned in the address of 000 to 270E. The number of the coil or register is considered as the position name. It will not shown in the actual data message, while data address will be applied. In the same network of Modbus, each slave will be assigned a unique address from 1 to 247. In the case where the master requests data from the slave, the first byte is a slave ID. In this way, each slave device will know if it should ignore this message or not after receiving the first byte. The second byte from the master is a function code. This byte will notify the slave which cells shall be accessed from the table, as well as read or write it. The most commonly used function code are listed in the table below. 01 is for reading single discrete output coil. 15 is for writing multiple discrete input coils. 02 is for read discrete input coil. 04 is for reading the analog input register. 03 is for reading single analog holding register. 06 is for writing single analog holding register, while 16 is for writing multiple analog holding registers. What is a CRC? CRC stands for Cyclic Redundancy Check. It is for the error detection of each Modbus message. With adding 2 more bytes at the end of the message, all bytes in the message will be used to calculate CRC. The receiving device will calculate CRC and compare it with the CRC sent from the transmitting device. As long as any bit received is wrong, the CRC will be different and causing error. The difference between Modbus RTU and Modbus TCP is that a Modbus RTU is over 485 bus connection and Modbus TCP is over Ethernet cable connection. For the normal application, the Modbus TCP is recommended. Now, let's have a look at the detailed comparison between the Modbus RTU and TCP. Modbus RTU is over 485 bus connection. The Modbus RTU device uses RS485 serial communication protocol. It is suitable for the poor working condition when the real-time requirement is not so critical. Meanwhile, it has obvious cost advantages as it is using shielded twisted pair. As for the Modbus TCP, it's over an Ethernet cable connection and based on a TCP/IP protocol. The communication data format follows the Modbus RTU data form. The Modbus TCP is connected with the slave devices via IP and port number. Slave address is not required. Modbus TCP is based on TCP/IP with a high traffic rate. applicable for the high requirement real-time application. Modbus TCP. When the robot has the Modbus TCP slave, the external master sends a connection request to the robot. And then it will be allowed to control the Modbus I/O through robot after connection is established. In the APP setting, find the Modbus parameter setting in the hardware and communication. Select Modbus TCP, edit the port number and click confirm. The robot controller IP will be the IP for Modbus TCP, while the port number should be the same as assigned with the Modbus TCP master. After the connection is established with the Modbus TCP master, it will be able to read and write on the I/O in the corresponding address. The input address shall be based on the Modbus address table. In the I/O monitoring page, click Modbus tags. We could also check the related Modbus I/O. Now let's watch a video about the Modbus TCP setting. First is the controller DO. In the APP hardware and communication page, we could set up or view the Modbus TCP port. Open Modbus poll and then click connection method as Modbus TCP. And the key in the IP and port number of the robot. Click connect and wait for the connection to be established. Click setup, select function code as 02, input the address as 8, data length as 10, click apply. Change the DO status from the app. We could read the DO status from the software. Then from the controller DI, select function code as 15, starting address set as 40, length as 10, and again click apply. Through inputting the signal status from the software, we could read the DI status from the app. Then for the Modbus controller integra, click display. Select unsigned integra. Click setup. Select function code as 04 and starting address as 96 and data length as 10. Then you can finish and click apply. The AO status in the software. We could read the AO status from app. For the sign integra, click setup, select function as 04, starting address as 112, data length as 10 and click apply. Set the AO status in a software. We could read the robot AO status from the app. The sign integer can be negative and positive.
Now the Modbus float. Once again, click Display, select 32 bits float big endian, click Setup, select function code as 04, starting address as 128, data length as 10, and click Apply. Set the I/O status in the software. We could read the robot I/O status from the app. The Modbus float integrates numbers after comma. Now the controller AI. For the integer, click Display, select Unsigned Integer, click Setup and select 16. Starting address 100 with input the register value. The status can be read from the app. For Modbus Sign Integer, click Display and select Sign Integer. Click Setup and select function code 16, starting address 116, length 10, click Apply. Input the register value in the software, the status can be read from the app. Now the Modbus float, click Display, select 32 bits float big endian, click Setup and select 16, starting address 132 with input the register value. The status can be read from the app. The status data of the robot, click Setup, select function code 04, set starting address as 406, length as 10, click Apply. In the software, we could read the robot real-time position data. Now let's see the robot as a Modbus master. In case of the robot Modbus as TCP master, the dynamic I/O function can be activated in a JAKA Zoo app. The robot is able to control the slave I/O via sending a Modbus command after the robot is connected with the external Modbus TCP slave. Configuration: add dynamic I/O in an I/O monitoring page. We could input the dynamic I/O name, the IP address of the slave, and the port number of the Modbus slave. Then configure the I/O address and quantity of the slave. Note that in app, DI is input status, DO is coil status, AI is input register, and AO is holding register. Now let's have a look at the communication test video for the Modbus TCP master and the Modbus slave software. Open Modbus POL. Click connection method as a Modbus TCP. Set the port number as 502 and click OK. Then the Modbus slave is created. Then you can click Setup, select the address type 01, starting address as 0, length 10. Then click Create and set the function code 02.
address as 0, quantity 10. Create another table with the function code 03. And finally, a fourth table with the function code 04. Open the I/O monitoring page. Click the Edit icon and add Dynamic I/O. From here, we could set the Dynamic I/O name. The slave can be any port number. Now, we set as 502. Same with the Modbus slave software. IP as the same as the Modbus slave IP. Configure the DI, DO, AI and IO starting address and less. All quantity as 8. In a case of no error as is occurred, means our Modbus master connection is established. We will need to check the coil status. In the software, we could edit the coil status. Then we could read its status from the app. As the coil is readable and writable, we could also edit the DO status from the app and monitor it from the software. Then for the discrete input status, edit and discrete input value in the software. The status can be read from the app. The status is only readable. The same for the analog signal, the holding register. They are both readable and writable, so we could edit status in the software and read it from the app. The opposite way will also do. The input register are only readable. Edit the input register value from the software. We could monitor its status from the app. Modbus RTU. The controller can be the slave of PLC, controlled by the PLC. When the controller is used as a Modbus RTU slave, the external devices should use the RS-232, RS-485 convector with active photoelectric isolation to guarantee the stable signal and protect the IPC from the interference from outside. In the APP setting, find the Modbus RTU parameter setting from hardware and communication options. Select Modbus RTU. The slave address can be set in a range of 1 to 128, while the baud rate, data bit length, stop bit length and polarity method shall be the same as the master assigned. In a case of the robot as a Modbus RTU master, its dynamic I/O can be used. The robot is able to control the slave I/O via sending request after connection is established. To configure its parameters, add dynamic I/O in an I/O monitoring page. Edit the name and address of the Modbus slave. The baud rate, data bit length, stop bit length and polarity method should be the same as the master assigned. Then set up the slave I/O address and quantity. After communication is established, the usage is the same as a Modbus TCP. Modbus slave address table. The first one is the controller I/O, which are the digital input of PLC. The starting address is from 8 to 128 in total. The second one, controller DI, which are digital inputs from the PLC. The starting address is from 40 and there is 128 in total. The third one, the controller AO, which are the analog input of PLC. Modbus Integra is starting from the address 96 and there is 16 in total. Modbus Sign is starting address 112, 16 in total, and the Modbus Float is starting address 128 and 32 in total. The fourth one, controller AI, which are the analog input of PLC. For the Modbus Integra, it's starting at address 100, 16 in total. Modbus Sign, it's starting at address 116 with 16 in total, and the Modbus Float starting at 132 with 32 in total. The fifth one, robot data, which are the analog input of PLC. The robot data include the status of the robot joint enabled, error, position, current voltage, speed, TCP position and speed, tool and the coordinates. For the details, refer to the Modbus slave address table. That is all for this class. Thank you for watching. Introduction of the welding instruction. The course will be divided into two big parts. Introduction of Move Z instruction and the introduction of the Move ZS instruction. The course duration will be around 10 minutes and the main goal is to be aware of the welding instruction. Let's start. Move Z instruction. Add and click the Move Z instruction. The setup page will be displayed. In this page, we need to set up a start position, end position, and any position. As the picture above, the TCP needs to move in a Z-shaped welding path on an inclined plane. Edit those 3 points position first. The start position is the origin of the welding path, and the end position is the terminus of it. And the any position is an N at any position in the welding plane. The welding plane Y positive direction is from the start position to the end position. And with this any position, we could define the welding plane, similar with the user coordinate system. Moving speed is the speed of Move Z motion. As the picture above, dimension A is the distance between the peak and through the wave. Dimension B represents for the distance between two adjacent peaks or through. In the case of unticked, the default angle of the Z motion is 45 degrees, means B will be twice dimension of A. Arc transition is for the peak and through motion. Peak pulse time, positive X side point means the position time after TCP reaches the peak, while negative is for top side. The TCP motion of Move Z is Z-shaped polyline as above. The arc transition can be both ticks or one only. Let's see the motion result of Move Z instruction. The first thing, we need to edit the start position of the Move Z. Second, we need to edit the end position of the Move Z. The any position is at any position in a welding plane. Then, we can click the Run Program button. before going back to the initial position before running the program. We can see that the move Z path is a Z-shaped polyline. The TCP will not pause when reaching the peak or through. Now what we can do is tick the move Z arc transition and run the program again. We could see that the robot will move an arc transition path at the peak of the welding line. Move ZS instruction. Click Move ZS instruction to pop up the edit page. As the picture on the right side, the TCP needs to move with a ZS shape path in an inclined welding plane. Edit the three positions that Move ZS required, which are start position, end position, and any position. The any position is at any position in the welding plane. With this any position, we could define the welding plane similar with the user coordinate system. Move ZS instruction. The moving speed is the speed of move ZS motion. Z width is usually no need to set up. Only when we tick the Z density, the default value of Z density is twice of the Z width. When ticked the rotation angle, input the angle that robot swing towards to one side. This value is 45 degrees when it's unticked. Arc transition stands for swing pause when reaching the maximum of the minimum position. Peak pause time, positive X or negative X means the pause time when the pause of RY reaching the maximum or minimum position. Separately, the TCP motion of move Z is a straight line, and the TCP will swing along with Y-axis. The robot requires high accuracy TCP when moving with move ZS path. Arc transition and peak pause time can be both ticked or on one only. Let's see the motion result of move ZS. So first, we need to change the start position of move ZS. Then, edit the end position of move ZS. The any position is any position in the welding plane. Set the Z width as a 10 mm, speed 50, Z density as a 20 mm, and rotation angle as 3 degrees. Run the program and move the robot to the initial position.
In this video, we could see that the TCP path is a straight line with a move ZS instruction, and it will swing along with the Y-axis while moving. That is all for welding instruction. Thank you for watching. Conveyor belt tracking instruction.
This course will be divided in 4 main parts. 1. Introduction of conveyor belt tracking. 2. Encoder wiring. 3. Instruction usage. And 4. Methods of programming. The course duration will be around 10 minutes and the main goal is being aware of conveyor belt tracking function.
Introduction of conveyor belt tracking application. This video is an overview of the application. The robot is tracking and gluing the product. Then it takes the product out. Let's watch it. Let's have a close shot at it. Now let's see the encoder wiring of the conveyor belt tracking instruction. On the picture on the right, the red rectangle marks the high-speed interface, which is for the conveyor tracking encoder connection. The table below is for the terminal rank connection. Pin 1 and pin 8 are for the 5-volt power supply positive connection. Pin 16 and pin 9 are for the ground connection. Pin 2 and 3 are for encoder phase A positive. Pin 14 and 15 for the phase A negative. Pin 4 and 5 are for the encoder phase B positive connection. Pin 12 and 13 are for the encoder phase B negative connection. Pin 6 and 7 are for encoder phase Z positive connection. Pin 10 and 11 are for the encoder of phase Z negative connection. This HSI for the ABZ encoder connection supports both differential signal type and single-ended signal type. The wiring method are as below. Regarding to the encoder with the instruction manual, wire it to the HIS according to its datasheet. For those encoder without instruction manual, identify the signal wires with oscilloscope before proceed wiring. For encoder differential signal wiring, the related signals of encoder shall be wiring as the picture and table below. Pin 1 to 8 connects to the phase A, B and Z positive and negative. Pin 4 and pin 5 connects to the 5-volt power supply positive and ground separately. The second type, NPN type, open collector output encoder and the voltage output encoder. NPN type open collector output encoder. The schematic diagram is as the left picture, the voltage output encoder. The wiring method is the same for the two types of encoders. The actual wiring is as below. Pin 1, 2 and 3 connect to the encoder phase A, B and Z positive. Pin 4 and 5 are for power supply connection. The third type, PNP type open collector output encoder. The PNP type open collector output encoder, the schematic diagram is as below. Pin 1, 2, 3 are for phase A, B and Z negative connection. Pin 4 and 5 are for 5 volt power supply connection. Instruction usage. Read the relative reading and status of the encoder. Note that conveyor instruction requires the controller version 1.5.12.25 or above to function. First of all, connect the encoder with the controller according to the procedure mentioned above. Second, use Modbus port to connect the encoder. Then, we could read the encoder reading and status according to the version 1.5 controller Modbus address table. Select and click Conveyor Belt Tracking Instruction. We could set up the pulse equivalent and conveyor belt direction in the pop-up window. Regarding the pulse equivalent, we need to read the encoder pulse start value and then the end value. Then calculate it with the distance conveyor advanced. The pulse equivalent equals to the pulse difference divided to the distance. There is currently two methods. The first one is to read the pulse difference and the pulse distance. Pulse from Modbus and distance with the caliper measured. The second is to calculate the encoder traveling distance per rotation. Then, read the pulse difference per the rotation via Modbus. Use those two for calculation. Regarding the conveyor belt direction, we could either use the manual input or position setting function. For manual input function, the X, Y, Z represents for the direction difference comparing with the origin of the user coordinate system. For example, 1, 0, 0 stands for the direction is along with the x-axis positive direction of the user coordinate system. While for the position setting method, we need to click Start or End position and set up the robot position. The instruction will calculate the conveyor direction according to those two positions. The conveyor direction is from the start position to the end position. Only position will be calculated regardless of the pulse. This method is recommended. The conveyor direction X, Y, Z will be difference value of end position deduct the start position X, Y, Z. Method of programming. The sample program is at the right picture. The robot will start from the joint movement, then, according to the pulse equivalent and the conveyor direction, start the linear motion and relative linear motion with the compensation for the conveyor motion. To achieve the tracking result, then wait for 1 second to repeat the motion. This is the program for the first demo video. First of all, set the outfeed and infeed slide cylinder as the initial status. Then, wait for the front load cylinder extend to fit in product, then start capturing while the product reaches the camera triggering position. Retract the front push cylinder. Wait for 2 seconds for the camera to process and start capturing. Wait for another half second for the camera feedback and read the X offset from that. Then compensate the X offset to the position offset. The robot will move the linear to the standby position in advance, which is the starting position of the circular motion. Wait for start tracking signal in, then recall the conveyor tracking instruction. Move with two semicircular paths, then the robot will move linear to the position above the center of the product. Open the vacuum and bring down it to pick up the product. At last, the robot will move to the fixed position to unload the product and retract the cylinder for the next cycle. That is all for the conveyor belt tracking. Thank you for watching.
Introduction to JAKA Zoo SE series. The introductions to force control function will be divided in two main parts. 1. Introduction of force control SE series, and 2. General use of force control. The course time will be around 20 minutes and the main objective is a preliminary understanding of the force control functions. This product is designed to use industrial-grade force sensors and integrate force control algorithm with independent and textual property rights to improve the perception of collaborative models and provide customers with a better human-computer interaction experience. As shown on the figure below, install the force sensor on the end flange of the robot and transmit the force value to the controller in real time. When the end effector of the machine receives an external force, the position of the end can be adjusted to adapt to the external force value. At the same time, customer can drag the position and posture of the robot more compliantly at the end of the robot. Zoo Force Control System includes APP robots, control cabinets, and force sensor equipment. The force sensor at the end flange of the robot are realized through the operation of the mechanical connection software at the end sensor module in the JAKA app. First, design the connection key between the force sensor and the end flange according to the actual needs. By connecting the key or setting the tool coordinate device, ensure that the X plus direction of the sensor is consistent with the X plus direction of the robot end flange. Then, the force sensor can be powered by the robot control or the user additional 24-volt DC power supply. Depending on the communication method for the sensor can be connected to the USB interface of the control cabinet for the serial communication, or through the network port for TCP/IP communication. If you choose sensor 1 or 3, you need to set the IP and port number in the app. For the specific setting method, enter the relevant sensor configuration directory. If sensor 2 is selected, IP and port number settings are not required. Force control automatic load identification function. When using a force control related function, you first need to set accurate load parameters. You can select manual input in the load setting or you can use the automatic identification function. The process is as follows. Set the starting position, enter the manual interface and move the robot to a suitable position. Click OK to exit. Set the end position when entering the manual interface. Only the 4th and 5th and 6th joints are allowed to move. And the range of movement is within plus or minus 90 degrees of the initial position. In the case of ensuring that the robot movement does not interfere, the larger the movement range, the more accurate the identification result will be. Click OK to exit the pilot operation, long press to set the starting position, return to the initial position and long press the pilot operation to confirm that there is no interference in the identification trajectory. To start identification, long press to set the starting position to the return to initial position, click Start Recognition, wait for a few seconds, the app will display the end identification result, confirm that the result is correct, and re-identify. Let's take a look at the video of using the automatic load identification function. Use the force sensor in the interface of setting the hardware communication and sensor. Here, use sensor 2 to set the start position. At the end position, the rotation angle of the joints 4, 5 and 6 must be within 90 degrees. Then long press to the starting position to move the robot to the starting position. Then long press 4 points to run and check for interfaces. And then long press to the starting position and move the robot to the initial position. Then you can click start to recognize, and the robot will automatically move from the start position to the end position. After the movement is complete, the current load will be automatically identified. Set the safety threshold in a sensor limit. During the movement of the robot, if the end of the sensor is set to be greater than the set threshold, the robot will immediately stop the movement to avoid danger or property damage. Let's have a look at the safety protection function of the force control. After disabling the sensor, configure the parameters in a sensor limit. Enable the sensor and start dragging on the teaching interface. When the detected force exceeds the limit, the display detects a collision and automatically exits the drag mode. Now we can try to run the program. The force control function is turned on in a program. When the external force is detected to be greater than the vertical limit, the collision will be displayed and the program will be stopped immediately. The force control traction test drive function enters manual operation. First, enter the configuration interface, where Fx, Fy, Fz correspond to the displacement in the 3 directions of x, y, z, and Mx, My, Mz correspond to the rotation in the 3 directions of x, y, z. By checking the checkbox in front of the direction, you can enable one or several directions. That is, if you can drag in the enable direction after dragging is turned on. The smaller the robot damping force is set, the lower the drag force the user needs to drag. But the smaller the resistance is, the better. It is recommended that the damping force is greater than 10 Newton, the damping torque is greater than 0.2 Newton meter, and the setting value cannot be 0. For the rebound, the robot can return to the original position before dragging. The larger the setting value, the greater the force required to drag the robot. Check the tool coordinate system in the force control coordinate system. Then drag the robot in the set tool coordinate system and check the world coordinate system. Then drag the robot in the robot base coordinate system. When the controller enters the drag mode for the first time after running, you need to check the initialization to compensate the sensor bias and load. And in the process of entering the dragging process, ensure that the end of the robot is not contacted by external forces. Otherwise, the compensation accuracy will be affected. After configuring the parameters, click OK and then click Exit to enter the drag and drop mode. Before entering the drag mode, the end of the robot should not be subjected to the external forces, otherwise it will cause sensor compensation errors and cause danger. Due to the temperature drift of the sensor, if the robot position drift in the drag mode, please exit and enter the drag mode to perform sensor compensation again. Do not use the towing test drive function. Please exit in time. Now let's take a look at the video for the force control traction test drive function. First, we need to configure the force control parameters of the traction window. Here shows the X and Y direction. The damping force is a 10 Newton. Select Initialize and the current force control returns a value of 0. If you choose not to initialize, you can see the real-time value of force control in the viewing interface. Drag the robot in the X-Y direction. Then we can observe the moving of the robot in the X and Y direction. Then we can add a rebound into the configuration. Open the drag again to manually drag the robot. After there is no external force, the robot will return to the initial position before the push of the robot. Turn off drag and reduce the setting of resilience. Turn on the drag again and the force required to leave the original position will decrease. Open the configuration parameters, cancel the ribbon and select the parameters in all directions. Then enter the drag mode robot and you can do position and a posture drag. The constant force mode can ensure that the contact force between the end of the robot and the external environment is within the range of the set constant force value. Constant force mode includes opening constant force compliance control setting, force control coordinate system constant force compliance parameter setting, and closing constant force compliance control. The configuration parameters in the constant force compliance parameter setting interface are consistent with the traction teaching parameters. The user can set the constant force value according to the desired contact force value. The size of the resistant force needs to match the stiffness of the external environment. Generally speaking, the greater the environment stiffness, the greater the resistant value is required. Due to the temperature drift of the sensor, it is recommended that after the robot runs for a period of time, make sure that there is no external forces contact at the end of the robot, and select initialization to recompensate the sensor. Now let's look at the video about constant force mode. Configure the constant force parameter in a program. The Z direction is 5 Newton and turn on the constant force control. The running program has a tendency to move downward in the direction of the tool in advance. Check the force in the Z direction on the manual operation interface. It can be seen that the force in the Z direction is about 5 Newton. The fifth force controls speed mode function. In input mode, when the end of the robot is greater than the control force setting, the robot will decelerate until the sensor detection value is less than the control force setting value. Speed mode includes opening speed, compliance control speed compliance parameter setting, then compliance control force and closing compliance speed control. Configure the speed ladder on the speed compliance parameter setting interface and select the size of the control force on the compliance control force interface. Now let's have a look about the speed mode force. In the program, you can set the speed compliance and the compliance rate parameters. Then you can run the program. Now we are going to monitor the speed using the Modbus TCP. So we are watching the address table for Modbus and we are setting the address to monitor the speed of the TCP. We can see that the speed of the TCP in a constant force is around 30. Now, when we apply a force on a force sensor, we can see that the speed is reduced. The sixth part, motion termination conditions. In the motion termination condition setting interface, check the direction to be monitored to set the upper limit or the lower limit. When the contact force values is less than the lower limit or greater than the upper limit, the motion neutral condition is triggered. The motion mid condition monitors the next motion instruction next to it. If the motion termination condition is triggered, the robot will immediately move from the current position to the end position of the next motion instruction. It is worth noting that all the parameters must be set to 0 in the constant force compliance parameter setting, and no direction must be checked. Now, let's take a look at the video using force control motion termination condition. Configure the motion termination condition parameters. Here, we choose the next first minus 5 Newton. The upper limit is 5 Newton. And then we can run the program. When the external force does not exceed the motion termination condition, the mechanical arm moves normally. When the external force received by the TCP is greater than the motion termination condition, the next motion instruction is terminated and the next motion instruction is executed. This is the end of this course. Thank you for watching.
Robotics education is changing for the better. The days of asking students to spend endless hours with their heads buried in textbooks and limited practical applications are coming to an end. This is in large part due to the fact that industry-leading robots have reached a level of accessibility in terms of affordability and usability. Collaborative robots are leading the charge here as they provide classrooms with the opportunity to use scaled-down versions of industrial robots with all the same functionalities in terms of safety and adaptable devices. Right out of the box, future robotics experts can practice simulating real-life scenarios using various methods of programming. Having studied the robotics education market, we've developed an education platform to accommodate a wide spectrum of robotics education. And today we'll be introducing the Mini Kobo education package. Here at JAKA, our education package consists of a Mini Cobot, which is a 6-axis collaborative robot with a repeatability of 0.1 millimeters and a payload of 1 kilogram. It has a reach of 580 millimeters and it connects directly to our mini cab through a power supply. The mini cab is a small robotic controller which has its own built-in Wi-Fi, 7 digital IOs, and is small and portable. The tool which we use in the education package is our own vacuum gripper, which connects directly to the TIO of the Mini Kobo for easy programming. On the platform, we have a trackpad with various learning outcomes. We have a palletizing platform, we have various shapes for waypoint teaching, and we have a TCP calibration tool for the most accurate tool calibration. Depending on your project, you can upgrade the education package and integrate a 2D camera which is capable of number sorting, shape recognition, and color detection. There are various options available for teaching robot motions. The most easy and convenient would be our free drive mode, which makes use of our free drive button to unlock all the joints and move the robot as easy as this. Position 1 and then position 2. Another method of teaching is by using our graphical programming, which is easy and intuitive. You can simply drag a motion into the programming block, click into it, and move the robot using our manual interface. Confirm, and there you have your point. JAKA robots also support a number of communication protocols, such as Modbus TCP/IP, Profinet, and finally Ethernet IP. With the Mini Kobo, we can simulate many applications, including assembly, pick and place, and palletizing, and much more.
J'ai fait la zone qui correspond à ce cadre. Donc là, si je m'approche, donc le robot, voilà, il va s'arrêter. À chaque fois qu'il arrive près de la zone, même au-dessus, par exemple, voilà, il va s'arrêter. Voilà. Voilà. C'est bon?
Ouais.
Voilà. J'ai mis le security point de l'autre côté du cadre, donc ça veut dire que le robot va pouvoir évoluer de l'autre côté du cadre. Et si jamais je veux revenir, hop, voilà, ça va bloquer. Donc si je tourne aussi, hop, voilà, il va bloquer. Et de l'autre côté, également, il va bloquer. Voilà. Donc il va pouvoir travailler que de l'autre côté, il ne pourra pas revenir. Voilà.